Okay, so good morning to everyone. I am Christina Heidemann and I am working at Luxembourg Institute of Science and Technology. And I want to present you some of the viticultural climate change adaptation strategies we are assessing in Luxembourg. So here's the agenda for today. So I want to shortly to introduce you to LIST, to the Luxembourg Institute of Science and Technology. Then I give a short background to the topic of climate change and viticulture. And then we go into the adaptation strategies. So we have the topics of sunburn, the targeted harvest timing for Cremant, the adaptation via late ripening cultivars, and the adaptation via fungus tolerant cultivars, and a quick outlook. So LIST is a young RTO which was created in 2015, but it has already more than 35 years of experience in research and development, as it all started in 1970. And it is active in 4 fields. So you can see it here. We have the environment, informatics, materials, and space. So me and also my colleague Daniel Molitor, we are belonging to the Agro-Environmental Systems Research Group, the AGRO group in short. And we are developing scientific insights and practical solutions for climate-smart agriculture. So we have expertise in environmental monitoring and pest and disease management, in pesticide reduction and sustainable practices, in climate change adaptation and impact assessment, and also in digital and precision agriculture technologies. And for viticulture, we have a long-term strategic collaboration with the Institut Vitivinicole, which is located in Remich in the Mosel Valley of Luxembourg. And together we are running research projects since 2006. And on the small picture, you can see the experimental vineyards at IVV. So now some background information. So viticulture is a very important socio-economic sector for Luxembourg. We have around about 1,250 hectares, and Luxembourg is producing 3.5 million bottles of Cremant de Luxembourg per year. And you should know that grapevine phenology, as well as yield and berry composition, are highly controlled by the meteorological conditions. What you could see in last years, and what will also be more in future, that we have a higher incidence of extreme events, for example, heat waves, and we can see a general decrease of precipitation in summer months. So on the right side, here you can see the monthly precipitation sum for the month of July from the years 18 to 24, as well as the average between 91 and 20. And this is all for Remich. So as you can see, there is the decrease of the precipitation in the summer months. So here, for example, in July, so it's usually much less than for the average. But we also have years like last year, 24, which was quite wet in the summer. And extremely was in 21, where we had a precipitation of 206.5 millimeters in July. So we had heavy rain events in July. So extreme events are not only heat waves, but also long-lasting rain periods in summer. And this can lead for viticulture to a high incidence of fungal diseases, which are causing many problems. So some more information, as you all know, I think, is that the increase of the annual air temperature is predicted for the future. But it's not only the increase of the air temperature. For viticulture, we can also see that all phenological stages are reached earlier, so the development of the grapevine is earlier. This means especially for the ripening period that it will take place in an earlier period of the year. And this means again that we have a twofold temperature increase in the ripening period because we don't have only the annual temperature increase, but as it's going into the warmer periods of the year, we have even more higher increase of temperature here. And that's why we also predict a decreasing length of the ripening period as the temperatures are higher here in this period. So this leads to the challenges in viticulture regarding climate change. We could see that we have higher temperatures, especially during the ripening period. And this means we have changes in the aroma profile of the wines. We have usually less acidity and a higher sugar content, which also means a higher alcohol content in the wine. And we have more extreme years. This means often it's too dry or it's too wet. And we have also, in our case, we have more sunburn and drought stress, which we didn't have that much before. So we can say that climate change is threatening the wine typicity and also the economic sustainability of the wine estates. And that's why we should test and implement adequate adaptation measures. So this is leading me to our aims for the research. So we try to develop some strategies for the winemakers to adapt to the new challenges in viticulture due to climate change. Of course, everything all under the Luxembourgish conditions. So we combine existing or developed models with up-to-date high-resolution climate change projections, and we want to support the wine growers in the application of adaptation strategies to safeguard their economic suitability. So in short, some of our investigation subjects. You will hear later more about the modeling in the phenological development under the climate change conditions. And in this presentation, we will see some of the strategies to control sunburn damage. Then we were testing harvest dates and in combination with the alcohol reduction and the impact on the typicity of the Cremant. We also wanted to validate the suitability of late ripening cultivars under our Luxembourgish conditions. And we characterize fungus-tolerant cultivars in 3 dimensions, so agronomical, ecological, and in the economic dimension. So let's go into the strategies to control sunburn damage. Just one slide for you to have a general view on sunburn on grapevine. So we have high temperatures and light intensities together with a high UV radiation, which can lead to sunburn of grapes. And in general, the heat waves are getting more frequent. So what we expect for our location is that we have an increase in the yield and quality losses due to sunburn. The symptoms of sunburn on grapes can range between brown or necrotic spots on berries, but you can also have complete desiccated berries. I have later some pictures for you to show how it looks like. The influencing factors are the variety, the developmental stage, of course, the water status of the plant at this moment, the wind, and also the vineyard management. And there are two main protection strategies, which are shading nets. And we also can take reflecting products, for example, kaolin. And what we did is that we had different treatments. So we tested one, the defoliation, and the application of kaolin. So this is the courtesan product. So we had one is the control. So we have no defoliation and no application of kaolin. The second treatment was no defoliation, but we had the treatment with kaolin. And then we have the early defoliation and late defoliation. And both we had one variant with no application and one with courtesan with the kaolin, so the reflecting product. And this we did also for the late defoliation. So here's some pictures how it looks like. On the left side, you have the non-defoliated variant. For early defoliation, you can see that the grapes are really well exposed. So yeah, we took away lots of leaves around the grapes. And the late defoliation was carried out later than the early defoliation. So you can see the berries are already a bit bigger and it's not that intensively like the first defoliation. And all this was carried out in 21 to 23 on the variety Riesling, which is a quite important variety for Luxembourg, also for Germany. And we did, of course, assessments in sunburn damage, but also of Botrytis cinerea, which is gray mold. So it's a very important disease for our cool climate wine regions. So that's why we were also assessing this point together with sunburn. So here you can see the results of 21 to 23, the sunburn damage for Riesling. And so these are averages from the 3 years. And you can see that so 1 and 2 are the non-defoliated ones. So they range between 1.9 and 3.7 of damage severity. The defoliation, the early one, you have here, the 3 and 4. And so then the late defoliation. And it's obvious that the late defoliation has a higher risk of sunburn than the other two variants. So it ranged between 7.6 and 9.9 of damage. And 2, 4, and 6 are the ones with the kaolin treatment. So this one could decrease the sunburn damage, but it wasn't in all years. So that's why we're saying it tends to reduce the sunburn. And the early defoliation is not that bad like the non-defoliated one, which has the lowest damage, but also the early defoliation is quite okay from the damage. Then we have the botrytis, so the gray mold, which we were assessing too in all the 3 years. So again, it's an average. And here we can see that it's the other way around. So the non-defoliation treatment, 1 and 2, has the highest disease severity. It was between 6 and 7. The late defoliation could already decrease the disease severity, so it's around 5%. And the early defoliation, it's around 2%. So it could decrease the botrytis damage a lot and in comparison to non-defoliation and late defoliation. So what did we learn out from this trial? The late defoliation always leads to the highest sunburn damage, and the courtesan, so the reflecting particles, tends to have an effect. And what is also very important for our region is the botrytis. So that's why for Luxembourgish wine growers, we would recommend to do an early defoliation because you have kind of two in one. So it can reduce the sunburn damage, but also the botrytis severity. That's why we would recommend this for our region, the early defoliation. Then we can go to the next adaptation strategy we were testing. So now we are going to the harvest timing for cremant production. Also here I have one small slide to the background. So Luxembourg is a very important producer for cremant. It's called Cremant de Luxembourg. And we also have some challenges here in the production of cremant. Because when you want to produce a cremant or sparkling wine in general, we have the problems that the acidity is decreasing because acidity is quite important for sparkling wine. That's why the trend goes towards an early harvest. But here you can have the problem that the grape quality is not optimal because it was too early and the aroma is developing a bit later. So it might be that you can preserve the acidity, but the aroma is not optimal. What we also have is that we have higher sugar contents in the grapes, which also means we have more alcohol in the wine. And this can cause problems with the second fermentation because the yeast then has too high alcohol and it won't ferment that good than with lower alcohol contents. And of course, if we have a second fermentation, we have even more alcohol in the product of the cremant. So we can see also here we have the problem that the typicity of the Cremant de Luxembourg is threatened by the climate change. So what we did is it was in 2022 and 23. We had two cultivars, Pinot Gris and Auxerrois. Again, it's very important cultivars for Luxembourg. And 2 days before harvest, we assessed again botrytis, the gray mold, and the maturity. And when we were harvesting, we were separating the yields into rotten and into healthy ones. So what we did, we had one harvest date, the starting point, it was harvest date 1. And the second harvest date was then the harvest date 1 plus 14 days. And again, the third harvest date was very late. It was then harvest date 1 plus 28 days later. So we had quite a long period of harvesting. And here I have just a small example of Pinot Gris because I don't want to show you all of the years and the cultivars. Because just like an example, you can see harvest date 1 was on the 6th of September in 23. Then plus 14 days, we had the 20 September of 23. And again, plus 14 days, we are already now in October. So it was quite a long range of harvest date. And what we can see then, that the maturity, it's in Grad Oechsle, which means the sugar content of the grapes. That is, of course, from harvest date to harvest date, it's getting higher. And the problem, what I was already mentioning, but the acidity is decreasing. So here you have, nearly the half of the first harvest date. So in the first harvest date, we had 11.1 gram per liter. And then in the last harvest date, so in October, it was just 6.1 gram per liters. Then we also had the part in the cellar. So it was a micro vinification with alcohol reduction. So in general, we took the same standardized procedure for all wines so that all the harvest states were treating the same way. So it was the same pressing program and everything was the same yeast, everything standardized. And yeah, fermentation was then done in around about 50 to 100 liter tanks. So it wasn't the big amount, but yeah, micro vinification. And then we have the three harvest dates. And what we did is that we took part of the second and of the third harvest date, and we reduced the alcohol content of these two wines to the alcohol content of the first harvest. So our question here was, is it better to harvest early, but maybe you have unripened grapes in terms of aroma? Or is it better to harvest later when the physiological ripeness is already reached and then to reduce the alcohol content? So that was a bit the question behind. And the alcohol reduction was done in cooperation with the Hochschule Geisenheim. So we took a hydrophobic membrane. So you can see this small machine here. So there's a membrane inside. So we have water and the wine that we want to do the alcohol reduction. They are flowing and only the alcohol can pass the membrane. So we have then an alcohol increase in the water and the alcohol content in the wine is decreased. And yeah, this we were doing two parts of these two harvest dates. So we can compare all the variants. So we have the harvest date 1. Then we had the harvest date 1 plus 14 days, like it was, and part of it alcohol reduced. And the third one, again, we had one part like it was, so with high alcohol content, and the other part we were again reducing the alcohol to the first harvest date. Then the crémant was bottled and a second fermentation was done. And this was during winter then. So we had 9 months of storage just because the minimum storage time for Crémant de Luxembourg is 9 months. And then we did a disgorgement of the Crémant. And then, yeah, maybe the most interesting part, the sensorial evaluation. And this was again done together with Hochschule Geisenheim. So here we had a trained panel. So they are tasting, yeah, maybe on a weekly basis, they are tasting wines. So they are really trained to this sensorial evaluation. And so here we have first the Auxerrois, and now it's the Crémant of 22. And here you can see the different treatments. So it was AUX 1 is the first harvest date. The AUX 3, it's the late harvest. And this one, the AUX 3 TE, was the alcohol reduction of the late harvest. So here again, you have also the harvest dates. So the first was on the 31 August of 22, and the third one was then in end of September, and this was partly reduced in alcohol content. And then you have different attributes which were yeah combined before, like there was mousseux, which is all very important for Crémant. You have sweetness, acidity, the bitterness, and some attributes that are fitting to the wine, like floral or apricots, pears. So the panel was trained to these attributes, and then they had to yeah, to say the intensity. So we have here the one is it's not you cannot perceive any difference until 10 that it's very intensively. And all of the attributes couldn't be separated, but the bitterness was perceived much more intensively, so significantly intensive in the third harvest date in comparison to both of the others, to the first harvest date, but also to the late harvest with alcohol reduction. And the same was done also with the other varieties, so with Pinot Gris. So here it's the same procedure. So again, it was the same panel. And we have again the Pinot Gris harvest date 1, the Pinot Gris harvest date 3, and this harvest date reduced in alcohol content. And here it's mainly the same. We have just one other attribute, which was red fruits. And again, it was only the bitterness that were perceived significantly more in the last harvest date in the Pinot Gris 3 than in the two other ones. So what could we learn? It was now just 1 year, so it was the Cremant 22. And from these results, we would say that, or you can see that Cremant with a high alcohol content, because it was harvested quite late, they are perceived as bitter. And we didn't had a significant differences in aroma when the alcohol content was reduced round about 2% of volume. But we also had no significant difference between the early harvest and the late harvest that was partly alcohol reduced in this sensory evaluation. What I can already say for the 23, so for the other year of vinification, that's the late harvest in Pinot Gris, so the last harvest date, there we had problems with the second fermentation. And so for now, we would say that earlier harvest should be preferred than to be too late for the harvest if you want to produce Cremant. But it's only results from 1 year until now. And actually the Cremant of 23, it will be tasted and evaluated end of this week. So maybe we will have new insights, when we have the results of this sensorial evaluation of the other Cremant. So now we go into another topic. It's the climate change adaptation via late ripening cultivars. So for cool climate wine regions, like Luxembourg, for example, one strategy could be planting late ripening cultivars from the southern regions, because maybe they weren't able to ripen here before. But now with climate change, it could be possible to ripen them here, as it's also getting warmer. So there was a test field which was planted in 2015. We have 13 different cultivars, and it's always 8 plants per cultivar. And there are different data sets we are assessing. So first is phenology, which means the developmental stages of the different varieties. This was already done since 2017. And all the others are data sets from 2018, because first they had to grow and get some grapes to measure, for example, the maturity progress. Again, the gray mold, Botrytis cinerea, which is very important for us. And then, of course, in autumn, we are harvesting them separately and measuring yield, the sugar content, and also the total acidity at harvest, which are the main characters for the wine grower if he wants to plant a variety. So first we go on the phenology. So here you can see the BBCH stages, which are describing the development of grape wine. So for example, you have 9, which is the bud burst. Then you go on to the development of the leaves, so 11 to 19. Then we go to the growing of the inflorescence. All around 60, it's the flowering process. Then the berries are growing, it's 70. And then we go into the ripening process from 81 to 89. So 89 would be ready for harvest. And our cultivars are Grüner Veltliner, Gelber Orleans, Alvarinho, Malvasia, Moscatel, and Viognier for the white ones. We have Pinot Blanc and Pinot Noir planted as reference. And for the red, we have Cabernet Sauvignon, Touriga Nacional, Tempranillo, Zinfandel, Cabernet Franc, and Syrah. So what we did here is that you can see the average delay of reaching a phenological state of these late ripening cultivars. And here everything is done in comparison to the Pinot Noir. So you can see it's all on 0 for Pinot Noir. And these are the data from 17 to 24. And you should read it like if it's green, it means that the phenological stage is reached early. And if it's red, it means it's reached later. So in general, we can say, or we can see that these, as it already says, the late ripening cultivars are mostly later in bud burst. So here for 9, in flowering, which is here, the 65, and also in the onset of ripening, as well as the ripening or harvest ripeness. But of course, there are also some exceptions like Grüner Veltliner. You can see it's completely green here. It's quite early in the first stages. In comparison, for example, to Cabernet Sauvignon, which is completely red here in the first stages, but also later it stays quite late. Some of them are really completely red, so Moscatel is always very late in all these developmental stages in comparison to Pinot Noir. And in general, the latest ripening of these cultivars here are Moscatel, Touriga Nacional, Cabernet Franc, Gelber Orleans, and Alvarinho. So these were the first data sets for the late ripening cultivars. Then we have the yields, which were assessed every year from 18 to 24. So these are the averages now. And we always have our references, Pinot Noir for the red and Pinot Blanc for the white ones. And in general, we have Zinfandel and Syrah for the red ones, where you can see that the yield is much higher than for Pinot Noir. For the rest, maybe it's a bit less, or like Tempranillo is quite the same than Pinot Noir. For Pinot Blanc or the white ones, we have mostly the same. Here, for example, for Viognier and Malvasia. And some we have a bit less of yield, like in Moscatel or Alvarinho. And for the acidity, again, it's the same. We are comparing to Pinot Noir and Pinot Blanc. And in the red, we have some that are quite high in acidity. It's mainly Zinfandel, but also, for example, Cabernet Sauvignon has a higher total acidity at harvest than Pinot Noir. And for the white ones, it's quite near the Pinot Blanc, but we have also exceptions that are much higher in acidity, which would be here Alvarinho mainly, and also Gelber Orleans, and one that has bit less acidity, which is the Grüner Veltliner from Austria. And here we have the maturity. So we have again the Oechsler, so the sugar content at harvest date. And we can see that we have our references around, 95, 93 grad Oechsler. And this is what we are searching for. And Tempranillo is quite the same, it's 95, but all others of the red cultivars, they have less sugar content at harvest. And here we want to search maybe minimum around 85. So here we have Zinfandel, which is in the average less than 80 grad Oechsler. The same we have for the white ones. Here the exception is mainly Moscatel, which has not reached 75 in average, but all the others are looking quite nice. It's mainly above 85 grad Oechsler. Gelbe Orleans is maybe 84. And then botrytis. So we are assessing weekly together with the ripeness. And again, the averages of 18 to 24. And here we have two that, a bit exceptional. We have Zinfandel and the Pinot Noir, which have quite high disease severities. And for the white ones, it's mainly here Malvasia that has higher incidence, but all the others are looking quite nice, even better than the references of Pinot Blanc and Pinot Noir. So what did we learn? For botrytis, we can see that Zinfandel and Malvasia are most susceptible, so we can compare the susceptibility to the one of Pinot Noir. And all the others were not susceptible to bunch rot. And for Zinfandel, it's mainly because of Drosophila suzuki, which is a fly. And this fly is laying the eggs inside of the berries. And then you can get kind of a off flavor, so it's smelling like vinegar. And you can have also potentially secondary fungi that can enter because they already have a door open into the berry. And here we could see that Zinfandel has a very high susceptibility to this fly. For the yields, highest yields were found in Zinfandel and Syrah, and the lowest in Moscatel, Grüner Veltliner, and Cabernet Sauvignon. But what we have to say is that Moscatel and Grüner Veltliner are here very low in vigor, so maybe it's also due to this fact that they are not that vigorous at this location here. And for maturity, so the sugar content is mostly lower than the one in Pinot Noir and Pinot Blanc. But if we have warm years, which are getting more frequent, all cultivars reach around about 80 to 90 grad Oechsler, which is quite nice. Only if we have late years like it was in 21, the maturity can be critical. So we can say that it is possible to grow late ripening cultivars, but maybe we have also another alternative, which we want to present you now. So the last adaptation measure, and it's also a mitigation measure, is the growing of fungus-tolerant PV cultivars. So what means PVs? PV is coming from the German word pilzwiderstandsfähig, which means fungus tolerant. So that's why we are calling them just briefly PV. And these cultivars are crossings between the Vitis vinifera, so the European Vitis species, and American or Asian Vitis species. And actually, we have the Plasmopara viticola, which is the pathogen of downy mildew, which is one of the major diseases in viticulture. And this pathogen has its origin in North America. This means that with co-evolution, the American and Asian species could develop resistance against this fungi. So that's why Vitis vinifera is crossed with those wild Vitis species. And then we have the first generation, but these are back crossed several times, again with Vitis vinifera, because in the end, the new variety, like it's showing here, should carry around about 85% of the Vitis vinifera gene, so here in green, because of the viticultural traits as well as the wine quality, which is much higher in Vitis vinifera than in the wild species. So these new cultivars, they have a reduced susceptibility towards major fungal diseases, so mainly downy and powdery mildew. And this allows roundabout for a reduction of 50 to 80% of fungicides. So this is quite important as we have the European Green Deal, and they want a pesticide reduction of 50% by 2050. And this is mainly only can be done by planting PVs because we have this high reduction of fungicides. So what are the adaptation advantages of these new cultivars? So one important point, of course, we have economical risk reduction under the more frequent weather conditions, which we could see very well last year in 24, where it was raining a lot and we had lots of problems with fungal diseases. But they could also be potentially more climate resilient, maybe due to other ripening characteristics or more drought tolerant. This is not yet very well assessed, so that's why we should focus also on these characteristics. And on the other side, we don't only have the adaptation part, but we are also able to mitigate the climate change due to reduced emissions. Because if we reduce fungicides, we also have less tractor passages in the vineyards. We have less transport and also less energy demand for fungicide synthesis. So I shortly present our project PV3, which means that we have 14 PV cultivars, which are compared to the traditional red cultivar Pinot Noir, and for the white ones, Rivana. And everything is done in 3 dimensions. So we are focusing on one hand on the agronomical part, then on the ecological part, but there's also economic analysis. So what we have the PVs, which are treated 2 times with fungicides. And for the traditional cultivars, we have 2 fungicide application regimes. So one is we treat them the same way as the PVs, so only 2 times. And the others, so it's always 2 rows. And the others are treated like usual, so it's around about 12 times per year. So with this project, our aim is to characterize these different cultivars because we want to support the wine growers in the decision of cultivar choice, because of course it's always a big decision for a wine grower to plant a new cultivar because of course it's for years. And our output will be information platform with some data sheets for those PV cultivars. So here I have the resistance against the major diseases. And we have 3 major diseases here. We have the downy mildew, we have the powdery mildew, and last year we also had black rot. And the blue line is always, so now I skipped the Pinot Noir and I compared here everything to Rivana to be not too overloaded in this diagram. So the blue line is the Rivana, which was treated like the PVs. So PV with fungicide application, which means 2 times. And the red line is the Rivana with the usual fungicide application, which is the normal application for the traditional cultivars, which is 12 times per year. So for downy mildew here, so it's the average of 2 years because the project is now in the third year. You can see that all PVs are around about 0, maybe 1 or 2 percent of disease severity, in contrast to the Rivana, which is treated 12 times. We are here around about 18%. And if the Rivana is treated like the PVs, so only 2 times, we have more than 30% of disease severity. For powdery mildew, most of the PVs are again here around 0 to 1%. So Cabernet Blanc, for example, here is one variety that it has a bit of powdery mildew disease, and only one had more around 2% of disease severity. And in comparison to the Rivana, which was treated usual, these two varieties had more. But if you treat the Rivana only 2 times again, it's much higher. And as I said, last year we had lots of different fungal diseases due to the weather conditions. And we had also black rot, which is not, which doesn't cause problems in every year, but if it's appearing, it can cause problems. And here we had quite differences between the peewees. So you can see both Rivana are around about 1% of disease severity. Some peewees are here, so again 0. But we also had some that had around 2, and especially those 3 which had quite high incidence of black rot disease. So we have Cabernet Blanc, Johanniter, and Sauvignac. Those 3 had quite high disease severities. So this is quite important then for the wine grower to choose. Because black rot is also not present in every region. So if this wine grower, for example, is in a region where black rot can cause problems, maybe you should pay attention then to this, to these susceptibilities. But it's always a local condition. So here we can already have difference between the cultivars, which is then important for the cultivar choice. One other topic of peewees is, of course, then the cost of plant protection, because, plant protection is also quite expensive. So here on the left side, we have the peewees in contrast to the traditional cultivars. And peewees, they have to be treated, or they were treated 2 times, which is causing around about 460 euro per hectare. On the other side, we have the traditional cultivars, which were treated 12 times. And for peewees, we just used copper and sulfur. And for the others, again, copper, sulfur, hydrogen carbonate, and phosphonate. So in total, we have 12 applications, which is causing 1,100 euro per hectare. So you can already see that for PV, we have a lower cost for plant protection. But it's not only about the costs. Of course, there's an environmental impact. So this was done by our colleagues, which were doing a life cycle assessment, comparing the PVs to the traditional cultivars. And here is the environmental impact. It's done in micropoints per kilogram grapes for the environmental impact. And you can see the PVs is at 12 micropoints and the traditional around about 35. So you can see that the environmental impact of the PVs is decreased. The same for the greenhouse gas emissions. So here in kilogram CO2 equivalents, again per kilogram of grapes of the cultivar. And here again, you can see the previous, the greenhouse gas emissions are decreased by planting PVs and yeah, making wine out of PVs. So coming to an end, I want to shortly give you an outlook on our next project, which just started this year. And as most of the last years were drier, so not last year, but those before, we wanted to focus on more drier summer conditions. And we have 7 work packages. The first one, we are assessing the adaptation via drought-resistant rootstocks. So we are assessing different cultivars on different rootstocks to see yeah, if there's maybe another choice of rootstocks in comparison to the ones that are usually planted at the moment. Then the second work package is on the impact of soil cover on the soil water conservation and grape physiology, because yeah, of course, in drier conditions, the soil water conservation is a very important point. So we have different covers. For example, we have a permanent grass greening. Then we have open soil, a permanent straw cover, a herbaceous greening, and this herbaceous greening without legumes. And we are comparing those ones. We have, for example, assessments of soil moisture in 0 to 100 centimeters. We are also measuring the sap flow of the grapevines. We have measurements of vigor, of yield, and of course of the fungal diseases. Yeah, and this started this year. For the third work package, we have a trial on field grafting. So we want to yeah, to change the variety mainly to PV cultivars, so to the fungus tolerant cultivars, and maybe without losing the established root system, because if you plant new vineyards, in the last year it was very hard to grow them, and you only have the first yield then after several years. So here it's a question if this field grafting, which is done wood on green, if this might be a better option. And the fourth work package, it's the adaptation via vitiforestry. So we are we are planting trees into the vineyard. And then the question is, how is the microclimate? How is the maturity? So of the grape ones which are really in the shadow of the trees, and those that are a bit beside. So here again, different assessments on microclimates. We have weather stations, also on soil moisture, the diseases, yields, and the ripening process. But still now the trees, of course, they are quite small. So this is a long-term project. Then we have work package 5, the adaptation via VT photovoltaic, which is a future project inside this project, let me say. So here the question is maybe we can put photovoltaic panels inside the vineyard to have energy and grapevines in one. Then there's a model part about future water supply and, of course, project management, data analysis, and reporting. So this is just a small outlook for you what we are doing the next years. So I'm coming to an end, and the two projects here were co-financed by the Gouvernement du Grand-Duché de Luxembourg, so the Ministère de l'Agriculture, Alimentation et de la Viticulture. And yeah, we always thank the Institut Vitivinicole for the very good cooperation. And I want to thank you for your attention. And I hope everything worked with the technique. And if there are questions, maybe you have to write them in the chat. And if not, my colleague is ready for the next presentation. Und next. Soll ich weitermachen?
Oh, it's the same screen.
No questions.
Okay, perfect.
No reaction. Soll ich fragen?
Man sieht sich nicht selber.
Mhm. Should we go on with the next presentation? Ich glaube schon.
Please, do you have it there in the same computer? Is it in the same computer, Christine?
Man hört sie einfach noch.
We did not hear any questions. Are there questions?
Any question?
You can hear some noise, but not a specific question. So Marco, maybe give me a sign if we should continue or no questions in the room. Okay.
Okay.
Okay. Wie hast du die Folie weitergeschaltet? Da muss man. Okay, ist okay.
Präsentation willst du?
Aber die sehen jetzt was ganz anderes hier. Hier auf dem Bildschirm.
Nee, die sehen das, glaube ich. Aber es wurde nichts gesagt, dass sie das nicht machen.
Jetzt habe ich. Aber
Ja.
hier. So you see now the next slide.
Ja.
So if there's no one complaining, so in fact, I don't see the chat at the moment.
Ja, man sieht's.
Okay.
Also ich sehe es nicht.
Okay. So after the very applied presentation of Christina, I would like to give you a few insight into our modeling approaches, and we are mainly focusing on grape phenology. And grape phenology is mainly temperature driven. This is always the message. So if the minimum needs in nutrients are fulfilled, then it's mainly the temperature which drives the grape phenology. And that's why it's working usually quite well to model grape phenology based on the temperature data. And the question is, why do we want to model phenology? This can be very useful if we think about pest and disease decision support tools. So usually the grapes are very susceptible to diseases in specific phenological stages. So it's good to know when those stages will be reached. And the consequence is also the plant protection is usually focusing on specific phases. So if we know which phenological stages are reached, we can also plan our plant protection strategy partly based on this. Although it's interesting if we know more about the heat demand of specific cultivars, or if they are very early in development or late, we can also use this information for selection of the right cultivars for specific location. And we can also um, use this to decide which cultivars we want to plant as a climate change adaptation strategy. Because the heat demand of different cultivars is different, and if the temperatures are increasing, we might adapt by selecting new cultivars which have a higher heat demand. And this is the consequence. We can use this for climate change impact studies. Exactly. We are usually following this approach you see on the left-hand side. This graph is showing that the phenological development is influenced by the temperature. If the temperature is too low, so if we are left of the A, you see, then there's no phenological development. If the temperature increases, I don't know if you see my mouse, the cursor. Okay, good. Once the temperature increases, then the phenological development is accelerating. And what we also assume is that if the temperature reach an optimal temperature for the phenological development, here the phenological development is maximum, then there might be a temperature range where the speed of the development is the same. And even if it's getting too hot, the, the speed of the phenological development is decreasing. This is a bit different than other phenological model approaches. For example, the Euclid index or the Winkler index, they are assuming that once the temperature passes threshold temperature, then it's a linear process. And this, for us, does not make sense from the plant physiology because, yeah, the speed will not get even higher if it's getting even more hot. I don't know, after 30 degrees or something like this. That's why we assume. So it's always a model is always an assumption that the reaction of the phenological development follows a curve like this. And we have we define three temperature thresholds. A is the temperature threshold, the lower temperature threshold. So below this threshold, there's no development. Then we have the threshold B, the upper threshold. This is the temperature where the phenological development has the highest speed, let's say. And there might be a heat threshold. Once the temperature passes this threshold, it's getting too hot for the plants, and then the speed of the development decreases again. And these temperatures are usually the daily average temperatures, and our approach here is to sum them up for every day. So this is the cumulative degree days, starting usually on bud burst of every day of the temperature sum for or the temperature of every day, and this is based on the temperature. So if we have I don't know, let's say 20 degrees on a specific day in and the threshold, the lower threshold is 10 degrees, then we sum up 10 degrees for this day. When we initially developed this model we used a broad date of calibration data. So we had observation data of phenological records for Müller-Thurgau and Riesling from different locations in Central Europe. So it's Luxembourg, Germany, Austria, and Italy. And we had observation data for all stages between BBC 809, this is bud burst, and BBCH 85 in this case. So once 50% of the berries are soft. And we defined the start date of the model as BBCH09, so but the date of bud burst. Mm, the idea was to apply this approach, and then we were searching for the optimal thresholds A, B, and C. And we did this based on the average normalized coefficient of variation. This is the standard deviation divided by the mean for all the stages. So we calculated the temperature sums using different thresholds, and we were searching for the optimized threshold triplet. So those three thresholds which were leading to the lowest coefficient of variation. So, for example, what you see here in this graphs, we were trying different lower threshold temperatures, for example, 3, 4, 5, 6 degrees Celsius, upper threshold, upper thresholds 15, 16, 17, 18, 19, 20, and so on. And the darker the color gets, the lower the normalized coefficient of variation. And you see here we reached the best model when we were using for, in this case, for Müller-Thurgau, 5. So 5 degrees, you see here. 20 degrees as the upper threshold, and the heat threshold we use 22 in this case. Or when we used 22, we reached the lowest coefficient of variation. We did this also for Riesling as a second cultivar. In this case, the thresholds were different. So the lower threshold for Riesling was 7 degrees, the upper 18, and the heat threshold 24. And based on this, we can create such phenograms for the specific cultivars. What we see here is the cumulative degree days with the three thresholds after BBCH09, so the bud burst. And these are the different phenological stages according to the BBCH scale. So how to read this? Let's say stage 16 is reached, let's say 140 cumulative degree days after bud burst, and so on. And this model approach is meanwhile used in different phenological models, parts of decision support systems. For example, this is Vitimeteo platform, which is running different plant disease models, but also the phenology model. And what you see here, these are different locations. And you see here for these locations and the different dates, which phenological stage is modeled to be reached. And if you click on one of those stations, this is an example of, from Austria, you get information about the meteo data, but also you get the information about the degree days of each specific day. So I selected this example because here we had a phase where the temperatures were very low, which means there were no degree days um, calculated because the temperature was below the lower thresholds. And what you see here in red is the cumulative degree day. So the example shows we had a phase when there was the phenological development, then we had a period with no development because it was too cold, and then a period again with some accumulation of the cumulative degree days. And these are the stages 0, 9, 11, and 12, and so on. What's also done based on this approach is phenology prognosis in Geisenheim in Germany. They are basing their model on recorded data, but they also include forecast data, usually for the next 7 or 10 days. And what they also do, they were using recorded data, forecast data, and also long-term observation data from the past. And based on this, so this was the observation of BBC 809. Then, based on recorded data and forecast, they make a prognosis on which date BBC age 13 will be reached. And what's quite nice here, they are also assuming for the forecast data and for the long-term data that it's getting on average 2 degrees warmer than on average of the periods in the past, or 2 degrees cooler. This gives you an information about the uncertainty of the model, especially if you are thinking about stages which are in 2 or 3 weeks. Um, it's difficult to it can be modeled, but the uncertainty of the weather prognosis is quite big. And this example I would like to show you here. This is an example. We had a look on the 17th of May on the prognosis. It was telling BBC H61 would be expected at the 12th of June. And due to the two scenarios with 2 degrees warmer and 2 degrees cooler in the forecast period and in the long-term period, there was a time frame defined when we expect BBC H61. And this was between the 8th and the 17th of June, depending if we have a warm or cool period in the following weeks. What we in fact observed was BBC H61 on the 13th of June. So the prognosis 4 weeks before was already quite precise. Of course, I selected this example because it worked very well, but generally, it's a quite helpful tool provided by Hochschule Geisenheim University. We also use this here in Luxembourg, although the model is included into it's called Witigis system, and it's running on the Acrometeo webpage. So this is a webpage of the on meteorological data provided by the agricultural administration. I just had a look on 24. So for every day you get the meteo data, but also the simulated phenological stage. So starting from 0, 9 until, yeah, it stopped here, but it actually it goes until 89 meanwhile, BPCH 89. What we further did is, yeah, you remember that we had different threshold temperatures for the different cultivars, but the idea was to unify this, to develop one model which is working for all cultivars. Because with this approach, you need different models for each cultivar. And what we did quite precise observations. So we have 7 years of observation of a high number of cultivars. In this case, all coming from the same vineyard. Um, and we tried the same approach again. In this case, we were working with the normalized standard deviation. And what you see here is the lower threshold and the upper threshold temperature for the different cultivars. You see that it's usually the summit of the curve is usually more or less in the same range, maybe around 10 degrees for the lower threshold and around 20 degrees um, for the upper threshold. But you also see in some cultivars the model is performing better. For example, for Pinot Gris, it's very precise. Also, Auxerrois, Pinot Blanc, Rivana, Elbling. Other cultivars like Merlot, the simulation is not as precise. Yeah, maybe it's a point we could discuss after why it might be the case. It might take too long since we are already coming closer to lunch break. Um, what we at the end did is to develop one model which is working for all cultivars, and the result was that we have lower threshold of 10 degrees and an upper of 20 degrees. And this table, in fact, just demonstrates you what's the difference between, so this is the standard deviation at 15 degrees, between the optimized threshold per cultivar and the standard deviation with the model using 10, 20, and 30 degrees as temperature thresholds. And you see on average the deviation is very low. So the message is in fact that we don't have a big influence if we use the optimized thresholds for each cultivar or if we are using the global or the unified thresholds in the Unifen approach. What is the result of the Unifen approach is we get such tables for different cultivars and for the different BBCH stages. And the starting point is always BBCH 09 in Riesling. So you see there's a 0 here. And how to read this, if we want to know at which temperature some BBCH 61 in Riesling is, we have to look in the table and we see it's at a temperature sum of 222. And you see other cultivars are reached BBCH 61, so beginning of flowering later than Riesling. For example, Sauvignon Blanc. 9 cumulative degree days later, but there are also some cultivars which are much earlier. For example, Chardonnay. And the colors here show, in fact, which cultivars are very early in development. They are green and they are very late. This is, for example, Sauvignon Blanc. Although what's interesting, Alpine, for example, is always very early, but it's reaching BBCH 89. So this we defined as a specific sugar content as the latest of all cultivars. So it's always difficult to say we have an early or late cultivar. Some are very early in some stages and late in other stages. What we meanwhile did is to apply also this approach to the new PV cultivars. Christina already explained to you quite a lot about the new cultivars. We were using a quite broad um, consortium of institutes from different countries. So we are still mainly in Central Europe, in Belgium, in Luxembourg, in Germany, in Switzerland, in Austria, and in Italy. And we had quite a broad range of cultivars. So in total, I think 13. And we were applying the Unifen approach on those observation data. So we had observation data from 3 years. At the end, we were focusing on 8 locations where we had the complete data sets. And this is how this table looks for the new cultivars which are included. So it's more or less, yeah, it's the same than for the traditional cultivars, the table I've shown you before. What I would also like to show you here is, this is in this case standard deviation at a assumed temperature of 15 degrees. So the greener columns or cells are in fact those where the standard deviation is very low. The more red it gets, the less precise the model is working. And just to show you, so in the early stages, the model precision is very good. Although usually around flowering, BBCH 61, 63, the simulation is very good. This is also coming from the fact that those stages are quite easy to access. So you just have to count the percentage of flower caps which are open, and then you have quite precise observation. Later in the season, you get some problems, especially in those stages which are around bunch closure. And this is quite a subjective observation if the clusters are already closed or not, and consequently the standard deviation increases at these stages. And although at the final stage of full maturity, the observation between the different observer from the different locations are different. And this is increasing the standard deviations. This is just one example to show you at different stages the different cultivars. For example, here, this is BBCH09. You see the earliest is Muscaris. The latest in this case is Pinotin, and this is the Riesling as a reference. This is still also in the PV cultivars. BBCH09 is the baseline, the starting point in for all cultivars. Also, you see here, ripe for harvest. Solaris is a very early ripening cultivar, so it's ripe for harvest very early. And yeah, Riesling as the latest ripening cultivar under our conditions, you see, is the one which has the highest temperature sum needed to get to full maturity. What we also try to do is to include the observation data from Montenegro. So we have observation data for Farnach and also some other cultivars grown in Montenegro. We have observation data from 24 and 25 and hope that we get more observation data also this year and try to incorporate maybe some of them into the Unifen approach, and this might be included in the decision support system, which is presently developed in the framework of the Montevitis project. And just to give you some references, so in fact, it was mainly the four references which we're using. Already more than 10 years ago, we developed the general model approach. We also applied this to climate change impact studies. This for me is one of the my favorite publications. So if you're interested, you might have a look that in fact the climate change temperature is in fact increasing the temperature in the ripening period twofold. Also, Christina showed you some results of this. So very important phenomenon. Then we did the Unifen approach using the same temperature thresholds for all cultivars 5 years ago, and just 3 weeks ago, the incorporation of the PVs into the Unifen approach was published. Okay, this was what I prepared for today, and I hope it was not too fast, and looking forward to questions from the audience.
Okay, thank you, Daniel. It was a great presentation, and I have one question related to the required time frame for this type of modeling. Does it 10 years of collecting the data is sufficient to have a precise technology models?
Yeah, it's difficult for me to understand you, but I guess I understood the question, how many years of observation you need. So the more the better. But yeah, it would be nice to have 10 years of observation, because then we have period or years which were extraordinary warm and cool. But if this is not the case, if we have data of 2 or 3 years from different locations, we might also be able to develop a model which is working quite well. Um, Yes. So ideally, if the observation data are coming from regions which have also differences in temperature, then we create kind of replicates due to the different locations. If we have three locations which are 5 kilometers from each other, then in fact it's not a real replicate because there's always yeah, they are not independent, those data sets. But if we have a broader uh, yeah, data from different regions, it might also work with maybe 3 years of observation.
And Daniel, thank you. I also have one question. Uh, Have you tried to use some kind of artificial intelligence or meta heuristic algorithms for determination these three thresholds in models? What is
I'm
your
quite sure that this is possible, but this is beyond my skills. But I'm sure that the model is not getting worse. It might get better, but yeah, it's a interesting topic, and also it's a bit limited. So we were using 10, 20, 30 degrees, but the sweet spot might also be at 9.43 Celsius. But this is beyond my Excel-based mathematic knowledge, but it's definitely could be interesting to optimize the model using more sophisticated approaches, let's say.
Hey, Daniel, this is Christoph. So, thanks a lot for the nice presentation. I would like to follow up on Marco's question regarding the calibration of the Unifan model, because I had personally quite some difficulties in calibrating this model. Did I understand correctly that you basically fix the thresholds and what you estimated during the calibration process is the total sum, so the temperature sum? Is this correct?
Yeah, it's always the temperature sum. It's accumulation of daily average temperatures with some thresholds, exactly.
Yeah, but you basically fix the thresholds. It's not that the calibration process itself involves changing interactively the thresholds and the sum to get to an optimal value of all.
I don't know if I understood the question correctly. So what we did initially, we were searching for optimized thresholds for all phenophases. So it might be the case that the temperature, the optimal temperature for bud burst is different than for flowering.
Mhm.
This might be the case. We tested this in the first publication. Of course, it's not getting worse, but it's getting more complicated. And we decided at the end to keep it simple and use the same thresholds for all the phenological stages. But I agree that the thresholds might be different for different phenophases. And
Yeah.
the model precision might also will most likely increase, but our idea was to keep it so simple that even the farmers might understand this. And yeah, if the thresholds are changing in each stage, then it's getting more complicated to understand.
So it would be maybe good if we can have a direct meeting later on, because I have really difficulties in calibrating your model when I consider also variable thresholds for each phases, for each variety. So if you add these complexities, the model does not calibrate quite well, for me at least. So it would be good to have a direct discussion maybe on that, how to improve the calibration process.
Yeah, definitely. Maybe we can search for a date for a meeting in the coming weeks.
other questions? No, I think there are no more questions in the room, so thanks a lot, Daniel and Christina again.
Okay. Enjoy. See you.
Thank you, bye. Bye.
Bye-bye.
Now it's time for a coffee break. Pausa, 10 minuta. Okay. 15 minutes, Natalia. 20
Again, thanks a lot for the nice introduction. And I'm Christoph Knight. And it's a pleasure for me to give a lecture in the summer school and also to start up this afternoon session with my presentation. And this afternoon session will be a little bit different from the morning session. So this session will be all about climate change and climate change impacts. So my idea here in the presentation is to basically introduce you to the basic concepts. What is climate? What is climate change? What are climate change impacts? What are the impacts in Montenegro? Then my colleague Peter will follow up with more detailed explanation of the mechanisms of the observed climate change for the European area. And then we will have at the end a presentation from Ricardo from Unifi, who will also show you novel methods to measure climate change effects. Okay, so let's start with my presentation. So a little overview of my presentation. I would like to cover the following points. So first, I would reintroduce the basic concepts. So what is weather? What is climate change, and what are the impacts of climate change? With examples. Then I would like to show you what was recently observed on the global scale, and what are the projections on the global scale for climate change. And then we will step by step find problems in our analysis, like, for example, model biases. And then I would like to shortly show you how to reduce these biases. We will have most likely more detailed discussion on this issue on Thursday. So I will not go deep into this issue. And then I basically try to increase the scale. So going from the global scale to the Mediterranean scale, and then to the climate change impacts of Montenegro. Okay, so let's start with some basic introduction of the concepts. So first thing, what is weather and climate? Is someone volunteering to explain or know what weather is, what climate is, and what the difference between those? Or okay, everybody is like looking right. Look, you're trying.
But it might be the short term and climate might be a long term. So that's the question.
Yeah, that's quite close. So you say for the online people, you say it's short term weather versus long term climate.
Yeah.
So that is partly right. And there's a kind of difficulty in the scales and how you basically define these scales. So what's long term, what's short term? So for our purposes, what weather is, it is the state of the atmosphere at a specific place and time. So for example, here I have the time series of Podgorica on the left-hand side, over 30 years of observations, and on the left-hand side, you only see the variations of temperature for a specific year, 2018. And with respect to the definition of weather, what weather is is basically the It's basically these ups and downs in the time series. So it's really what's the status, what is the temperature, what is the precipitation, what is the air pressure, radiation at a specific place for a specific time. The climate, on the other hand, if it would work. Okay, I think the pointer is not working that well. Does someone know how I can put the, okay, it's this way, yeah, okay, it works. Okay, so the climate on the other side is, as you say, it's a long-term observation. In our framework, it is the temporal statistics of the weather system. So on the on the right hand side, we have these ups and downs, which we say they represent the weather system. And the statistics here, for example, is the 30-year average seasonal cycle. Okay, so this is one statistic of the weather system, and this statistic we call climate. On the left-hand side, we have a long-term time series of daily of annual average temperature, and this is also statistics. So we can call this climate. Now, there is a specific ambiguity or vagueness in the definition of weather. So we say that it's a state of the atmosphere at a specific place and time. However, if we talk about weather, we call weather also the daily average temperature or the daily average precipitation, which is to a certain degree a kind of statistic of the weather system, but we still call this weather. So this is, again, some confusion that arises when people discuss weather or climate. Where is this boundary between weather and climate? And to somehow lose this difficulty, the WHO, the World Meteorological Society, has defined the weather and the climate as some statistics that was observed over 30 years. So they define reference periods over 30 years, and they say this is climate. However, it gets also more complicated if you go deeper into the definitions of climate, because the climate definition itself is also bound to a specific scale. So you have a spatial scale and you have a temporal scale, and both are combined. So here I have just listed 4 of the scales that you can, spatial scales basically, that you can look up. You can, and the associated atmospheric phenomena. So for example, we have on the global scale, if we talk about climate, we usually mean periods and averages over centuries and millennia. So for example, what happened to the last ice age? Then we have a climate scale that we use, or that we usually talk about when we talk about climate change. And this is a scale between, that is called the meso and the macro scale. So between local areas, cities, up to whole continents. And there we have phenomena like the ENSO phenomena, climate change, of course, city climate, for example, also that is under these scales. And if you think, for example, at what could be defined as climate on the continental scale, and what could you would say, yeah, okay, it's maybe the 30 years period, 30-year averages. But if you go to the city scale, what people refer to climate would be, for example, something what's the climate, the average climate in the city for the last 5 years. So they see there's a difference in the spatial and temporal scale of what you talk about when you talk about climate. And this becomes more apparently when it goes to the microclimate, and the microclimate is basically everything that is below 1 kilometer scale. And microclimate, for example, also involves the room climates, the climate that is inside of this room. And you can, I mean, it's intuitive that when we talk about the climate in this room, we will not talk about the 30-year averages of the climate in this room, because 30 years maybe this room will be completely different. When we talk about the microclimate in this room, we talk about maybe the hour or even the minutes that we observe. So it's not so easy to distinguish between weather and climate in this regard. And at the end, it always depends on the problem that we study. Should we study the continental scale climate change, global scale climate change, the room climate? And this is all bound together and defines what climate is. However, what we would like to analyze or learn here is basically what we call climate change if we go to the continental scale. So what happens outside due to anthropogenic climate change? And one might say the climate is something that is constant in time. However, and if you go on a period like 10 years or 5 years, you are quite correct. So over 5 years or 5-year averages, you don't see a strong difference in the temperatures. However, if you go on a longer scale, and here I have observations of the last more than 10,000 years of temperature on the global scale, you can see that the temperature actually changed quite strongly over the past 10,000 years. And it's interesting to see that these, or you see here warm periods and also colder periods. And it's interesting to align these to specific events or changes also to the humans. So for example, at the end of the last glacial period, so when we came from quite cold periods to warmer periods into the Holocene warming, this is basically the period where people develop or humans develop agriculture, and they stay at a specific point and not moving around. So this was also contributed due to climate change. And then we have periods like the Roman warming period here that was around 2000 years ago. And these were quite good climate conditions that also helped the Roman Empire to move across the Alps, for example. Then we have the medieval warm period, and after that, a colder period that is called the Dark Ages, where you also, due to the bad climate conditions, we have bad conditions for the humans themselves. So there are already quite fluctuations in the climate system for the past 10,000 years. And the question is, what are the main factors that contributed to these variations? And there are in general 5 different factors that we can name here. One are the orbital parameters of the Earth. So one is eccentricity. The eccentricity here, which is basically telling you how far is the Earth away from the Sun in its orbit. So if it's closer, it's warmer. If it's far further away, it's colder, of course. Then we have the obliquity, which is the angle, basically the angle of the Earth rotation axis to the orbital plane. So this is basically what's causing our seasonalities. And then we have the wobbling of the Earth's axis around this obliquity, and this is called the precession. And all these 3 factors basically act simultaneously, and they change the climate on time scales between 10 and 100,000 years. These are the famous language cycles. You ever heard of that? Then we have another factor that influences the climate, and this is the solar radiation. We know quite well that there's a fluctuation in the solar intensity that changes, like, or has a frequency of around 11 years, called the Schwabe cycle. However, if you look here on the left-hand side, over longer time scales, you also see that the intensity of the sun also changes, not just on 11 years period, but also on the longer period. So we have warm phases and also or high intensity phases and less intense phases. Then, of course, we have the volcanic activity. So volcanoes introduce a lot of soot in the atmosphere, and they block the sunlight. So we have direct cooling effect, but they also emit some amount of CO2. So on the longer term, we have a warming effect. And here you can see a picture of the eruption of the Pinatubo in the Philippines in the year 1991. And if you look here at this time series here of temperature, you can see that due to the eruption of Pinatubo, we have here global average temperature drop small. So this can be associated to the Pinatubo, so colder global average temperatures after 1991. And the fourth impact on the world climate is due to the ocean circulation. The ocean circulation is basically like the atmosphere, the transport phenomena that transports warm waters from the equator towards the pole, where they cool down, sink to the bottom, and then go back in the cycle. So similar like the atmospheric circulation. However, this circulation is much, much slower. So the circulation of the ocean is between 1 and 1.5 thousand years. So if you try to track an atoll that you put into the equator Atlantic and then follow its path through the ocean circulation, it re-emerged in this equatorial Atlantic after 1 to 1.5 thousand years. So any change that is introduced into the ocean will appear in 1,000 years, and also any change that we induce to the ocean will take some time to take place in the ocean. And the last and for other latest warming, most important factor is the greenhouse gases, or the greenhouse gas concentrations. So the greenhouse gases, I think you're well aware how they work. So they work basically like a blanket that you put on the earth that re-emit long-wave radiation or heat radiation from the surface back to the surface, and simply like a blanket, leading to an additional warming. We know quite a lot of greenhouse gases, but here I listed the most important. So it's carbon dioxide, methane, nitrous oxide, sulfur hexafluoride, and also water vapor. Usually water vapor is left out of this list because the effective warming effect of water vapor is quite low because it's so quickly excluded or removed from the atmosphere. So you have a residence time of water vapor is about 2 weeks, while introduced carbon dioxide will stay in the atmosphere for at least 50 years. Okay, then a list of, so this is climate change. The question is, what are the impacts of climate change? And there are quite a lot of impacts. And here I would just give a short list of different impacts that you can study, defined by the different systems of the Earth. So we have, for example, the atmosphere, and climate change impacts on the atmosphere are higher temperature, more rain, more storm, for example. So everything that changes the atmospheric condition. Then we have changes or impacts in the hydrosphere, flooding or droughts. We have changes, of course, in the cryosphere, so the ice shield of the Earth. So we have melting of ice shields and glaciers. We have changes in the biospheres that are quite complex, both because, for example, we have the space of living for certain species might become smaller, but also like for pests, we have, due to climate change, favorable conditions for these pests in regions where they were not established previously. So we have new pests due to climate change in new regions. And then we have quite a lot of impact on the anthroposphere, so on the human system. And these are, for example, agriculture, for example, due to droughts, or due to changes in frost frequency, for example, that can damage crops. We have health-related issues. So we have in the recent year quite a lot of people that died due to heat extremes, summer heat waves. Then we have damages to the infrastructure, both, for example, due to increased sea level rise. So coastal areas are affected or impacted by climate change. But we also have, for example, influences due to extreme events that could damage tracks or of trains or cars. And we also have impacts on tourism, where, for example, winter tourism gets less attractive because we have lower days of frost, so we have less snow, and you need snow for winter. Okay, and then we have the whole impact line for the economy. So everything here in the anthroposphere is also then related to the economy. So health issues have an impact on the economy. Agriculture has, of course, an impact on the economy due to changes in trade and the crops that are traded. Tourism, of course. So everything is connected, and there's a huge list of impacts that you can just name. Okay, and climate change, of course, impacting most of the Earth. Okay, so let's have a look what climate change has already done to the planet. So what I show you here is the temperature change in the last 30 years from 1991 to 2020 compared to the 30 years before. So what we can see here is that we already have quite a strong warming on the globe. What I would quickly mention here are 4 different observations that you can make on this plot. So first observation, in general, we have a stronger warming over the land than over the ocean. This is simply due to the different heat capacity of the ocean and the Earth. So the ocean, due to also the ocean circulation, has a much higher heat capacity, so it needs more energy to have the same temperature increase in the ocean. Then we have a north to south gradient. So the global south has less heating than the global north. This is also due to the different heat capacity of land and ocean, because the northern hemisphere has just more land and less water. Then we have a peculiar thing that is called the Arctic amplification. And this is the strong warming that we have, especially in the northern poles, but also to a much lesser degree in the southern poles. And this Arctic amplification has several reasons, and the main reasons that you can name here are, for one, the atmosphere over the poles is less thick, so we have a lower atmosphere, so it takes less energy to warm a smaller atmosphere, of course. Then we have what is called the ice albedo effect. So icy surfaces, white icy surfaces, reflect a lot of sunlight, while darker surfaces, so the surfaces below the ice, can absorb the sunlight, transform them into heat, the one-way radiation. And if you have the melting of ice, you have the dark surface, and you have an additional feedback effect that then accelerates the warming. And the last major contributor to this Arctic amplification lies in the thermodynamics. It's simply that colder air needs, and you just need to take my words for granted, colder air needs less heat to get the same temperature increase. So for cold air to increase temperature by 2 degrees, you need less heat than if you have warmer air. But this is just thermodynamics. So these are the 3 main contributing factors to the Arctic amplification. And then one interesting thing are that we have actually areas on the globe that are not warming but cooling. And these are usually over the northern and southern oceans. So we have here cooling pools around Antarctica, but we also have a cooling pool here close to the Greenland ice sheet. And these coolings are basically due to changes in the ocean circulation. So here we already see that the ocean circulation is changing due to climate change, and this change caused this cooling effect. Okay, then we can do the same analysis with precipitation. And the first thing that you can see here that of precipitation, we have much more variability because, of course, precipitation is much more variable. So we would anticipate that also the changes are stronger. What's interesting here is that close to the equator, we have these bands of high increase and high decrease. And these are basically indicator for that the circulation system, the global circulation system is shifting. So the main contributor here is what is called the in a tropical conversion zone, which is basically a rain band that is close or circumrounds the equator, and this rain band moves through the seasons northward and then southward. And in this rain band, it's called rain band, you have a lot of precipitation. So when we see here these precipitation change pattern, that basically in the northern hemisphere we have more precipitation, and in the southern hemisphere we have less precipitation. We could identify here that this intertropical conversion zone is just moving due to climate change farther north than it does for south. This will create these patterns. And also quite problematic here is that we have drying over quite important ecosystems of the world. So we have a strong drying over the Amazon rainforest observed. We have a strong drying over the African rainforest, and we also have strong drying here over the eastern part of China. So these are really damaging ecosystems, and also people. I mean, eastern China, we have 1 billion people living there, close to the eastern coast of China. Okay, so the question is, how does the future look like? And here I would just quickly introduce you to the tools that we use for estimating the future climate change, and these are global climate models. Global climate models are numerical models. The basic concept that they use is they divide the globe into grid cells and then simulate the flow of energy, mass, and momentum from one grid cell to the other, of water vapor, of dry air, and then in each grid cell we have certain processes that cannot be solved by this simple movement from one grid cell to the other, and these processes need to be parameterized. And just to give you an impression what these processes are, these are turbulence, for example, so wind that's turbulent around a mountain, for example, clouds, precipitation, radiation. All these processes need to be parameterized, so they are not solved by physical dynamical equations. They need to be estimated and parameterized. The typical resolution that is quite interesting of modern global climate model is between 50 and 200 kilometers. So if you consider Montenegro, for example, a global climate model will cover Montenegro by, I don't know, 5 or 6 grid cells. The temporal resolution is in the 10 minutes to half an hour. And despite these costs, temporal and spatial resolution, due to the fact that so many grid cells at the end and so many processes are involved, we need supercomputer to run these models. And interesting, if you look into what is available, how many models are available on global scale, how many global models are available, you see that we only have like 30 different global models that are used, they maintained and developed by different research centers. And all these models are basically trying to coordinate their simulation efforts in a project that is called the Coupled Model Intercomparison Project. So usually we take model simulations that are published under this framework because they are coordinated. Then if we go to the future, we also, to drive these models, we also need their major driver. And this driver is the greenhouse gas concentration. These greenhouse gas concentrations for the future needs to be somehow projected. So you need to have some idea how will the socioeconomic world will change in the future. And for this, people designed different storylines, and these storylines are called here SSPs, for shared socioeconomic pathways. They are socioeconomic pathways. And these storylines are then taken by modelers that run socioeconomic models, and then translated with these models into CO2 concentration or CO2 emissions for the future. And for me, it's quite interesting to see what are these storylines that are behind socioeconomic developments. And there are 5 different storylines. One, the SSP1, is the sustainability scenario, that the world is basically moving slowly towards sustainability. It's really what is also called taking the green world, so it's the best possible future we will have with regard to climate change. So we have strong efforts to reduce the emissions and also reduce inequality. Then we have the middle of the road scenario, which is basically a continuation of our current pathway into the future. Then we have a scenario that I would say 15 years ago, I would think would be very, very unlikely. And this is regional rivalry. But the world right now looks quite like the regional rivalry as it's depicted here. So we have less international cooperation. The environment is not the most important factor. We have strong nationalism. Then we have the inequality pathway, high inequality between countries, but also within the country. And we have some technological development, but this technological development is more for the route and less contributing more to the inequality. And then we have, of course, the most devastating pathway with regard to climate change, and this is just abandon all alternative energies, just pay fossil fuel for development, and this will actually then translate in the worst possible climate change. And here on the top, you can see for each of these 5 SSP scenarios how they end up in terms of the per capita CO2 emission. So the SSP5, the fossil fuel development, will have a quite strong per capita CO2 emission, while the sustainable development road will have the lowest. And it also will have a peak emission around 2050, and then reduce emissions. Okay, so then one word of caution when analyzing climate models, because climate models are uncertain, and here I like to refer to a site from what Niels Bohr says, and he says that prediction is always difficult, especially if it's about the future, and that's exactly what our climate models do uncertain prediction of the future. There are certain sources of uncertainty, and I would just like to list these uncertainties here. So we have one is the natural variability, the weather system is a aquatic system, so we have some fluctuations. We also have the impact of the solar cycle, volcanic activity, the ocean that has slow impact on the atmosphere, and this will all cause a natural variability. This has to be taken into account if you analyze climate models. Then we have, of course, the scenario uncertainty. So of these 5 storylines or pathways that I presented, we don't know right now which of these pathways we will take in the future. And the other thing is the model uncertainty. So even though the models are all based on the same physical equations, use similar parameterizations, they still simulate a chaotic system. So even small differences can result in different projections. And here I show you from precipitation projections, precipitation simulations for Africa, and you see already here that there's quite some differences. However, I have this picture also for the whole globe, showing you here for 10 different models, how they simulate a 2-degree world. And you can see that even though all these models have the same emissions, so they have the same greenhouse gas concentration in the atmosphere, you have quite a different change signal. So we have some models that have a strong cooling pole or warming pole. Others have none warming pole at all. We have some models that have strong Arctic amplification. Other models have nearly no Arctic amplification. So there's already quite some difference for simulating a 2-degree world. And the 2-degree world in this context is simulations with the lowest possible greenhouse gas concentrations. If we go to higher greenhouse gas concentration, these differences get even bigger. So this is how the models simulate a 5-degree world, and this is quite quite anxious because we have, for example, one model that simulates an Arctic amplification that is somewhere between 10 and 15 degree temperature increase until 2100. So even though the average increase of the whole globe is 5 degrees, we have areas that are 10 or 15 degrees in these models. So I will skip this one. So one difficulty that we face if we go now the next step from climate change to climate change impacts is that the impacts are usually not interested in the temperature change. So most climate change impacts, like for example, how flowers develop or how plants develop over the year, or the melting of the ice sheets, is not depending whether the temperature increases by 2 or 3 degrees. It is important how much the temperature or how high the temperature is. So does a 3-degree temperature increase mean we end up at 0 degree, or does it mean we end up at the 2-degree absolute temperature? And this makes a difference whether the ice melts or not now. Now, we can estimate how well our models simulate the actual climate. And this is what I've done here. So here I show how the models simulate the annual average temperature compared to the observations. So minus the observation. So what you see here is what is called the temperature bias. Blue means that the model simulates colder than observed, and red means that the model simulates warmer than observed. And what you can see here is first, like these are 4 different models, and every model has different patterns. So every model seems to simulate different bias, has different errors. And also, if you look at the magnitude of these errors, these are somewhere between -7 and 7 degree bias. So one model is on a certain area 7 degree to warm, and another area 7 degree to cold. This is already a magnitude of error that is similar to what they project for climate change. Okay, so at the end, the model could be 7 degree too cold and results or simulates a projected temperature increase of 7 degree, so end up at 0 degree, or it can have a temperature bias of 0 degree, so no bias at all, and simulate 7 degree temperature increase, so it ends up at 7 degree future absolute temperatures. So it really makes then the difference on the inputs. So what we need is we need to remove these bias somehow. Otherwise, we cannot use these models for climate change impact studies. And this is done by so-called bias adjustment. So there are several reasons why these models simulate a bias or create a bias. It's simply because they are just approximating the world, and the degree in which they approximate the world in their simulation then results in a certain bias. There's a statistical definition of the bias. So the bias is basically the estimated, and estimated here means long-term simulation of a quantity, like for example, the long-term temperature minus what is the observed temperature. The difficulty with the bias is that, as we have seen in the previous slide, the bias is nothing that is constant over the whole globe. It's also not constant in time. So we have basically different bias in the different distributions. So if, like here, for example, you plot the temperature distribution of a specific point and compare in red, and then compare it to observed, we can see that it's not just the average temperature, but it's a whole distribution that has a bias. Then the bias is different in space. So like you can see here, this is precipitation bias and over Bangladesh, and we have areas that have a negative bias, and we have areas that have a positive bias. So if we perform a bias adjustment, so fixing of this bias, we need to apply it for every grid cell separately. And also the bias is different for every variable. So they have different bias temperature and different bias interpretation. And this needs to be all taken care of. One important thing is the framework or the viewpoint that we have here. So I told you about the uncertainty. And one could say that this bias might be also an uncertainty. It could just be considered in your analysis as an uncertainty. But since we can pin them down to really inefficiency or inaccuracies in the model themselves, we can say that this is a systematic error. And systematic error is not statistical, it's not this uncertainty, or we don't interpret this as uncertainty, so we can remove. We should not consider this as an uncertainty. Okay, so how is this bias adjustment done? I think there's also on Thursday a presentation that gets into more detail here. So the prerequisite for bias adjustment is, of course, we need observations that we compare these model simulations to, and then calculate some values to remove the bias from the simulation. And how we do this is, mathematically speaking, mainly we have a simulation. And this simulation needs to be transformed with some function that is called the transfer function into a new simulation value in a way that the observation or that the distribution of the transformed variable has the same or at least similar distribution like the observations. And there are several methods that you can use, and usually you have a pragmatic choice. So what is your experience? How much computational power do you have? This decides which method you use for bias adjustment. And Here, just to give an intuitive understanding how these methods work, I have got it here in black the distribution of temperature of a certain grid point. It's not interesting which grid point. Observations, in fact, and in red what's simulated. And one method would be simply to move the red distribution towards the center of the black. The distribution should just shift the distribution. Then we can be, at least for temperature, a little bit better. We can also adapt the deviation, the standard deviation of the distribution to look more like the observations. And then we have also methods available that directly map each point of the distribution to the distribution of the observation. And there are also additional properties that use bias adjustment can have, like preservation, or they can adjust multiple variables simultaneously to keep the correlation consistent. Just to show you how modern bias adjustment methods work, how the situation looks before and after the bias adjustment. I show you here on the left-hand side the temperature bias of 4 different global models. On the right-hand side, the precipitation distribution and precipitation bias. And both are quite huge. The precipitation bias is even stronger, I would say, at least from that. And after bias adjustment, you can see that there's, for temperature, there's nearly no bias at all. And for precipitation, since precipitation is much more difficult property to observe and also to adjust, we still have some small bias. Okay, so now we can go, after we know now the general framework, what we did with the climate model and how we adjust them to use them in the context of climate change impacts. We can go finer into scale. And here I would first go from the global scale into the Mediterranean scale. So what are the changes in the Mediterranean? And here, just as some kind of appetizer, I show you on the left-hand side, on the left-hand side, the temperature change, on the right-hand side, the precipitations change, both for the whole globe, and what this change means for the Mediterranean. And what we can see for the temperature is, again, for 3 different mission scenarios or storylines. And we can see that the Mediterranean temperature increase is quite similar to the global temperature. So we are far away from the Arctic. We don't have an Arctic application. We are also far away from any warming hole. So the temperature change in the Mediterranean follows, at least for the respective future projections, quite closely to the global. However, if we go to precipitation, we can see on the global scale, we would have a general increase of precipitation, which is quite intuitive because warm atmosphere can carry more water. More water in the atmosphere means we have more rain. So on the global scale, warmer global scale, we have more precipitation. However, this precipitation is distributed throughout different areas of the globe. And the Mediterranean area is an area where we would have, in general, a decrease of precipitation, which is already quite difficult for the agriculture in the area. So if we go to what is observed in the last 30 years, we can see that we have already a quite strong warming here of the Mediterranean area. The strongest warming was in the summer season, and we have there already a warming of 2.44 degrees. So the already observed temperature increase in summer in the Mediterranean is already a 2-degree world. So this is actually the state we have right now. On an annual scale, we have a temperature increase of roughly 2. Precipitation, we already see the projected drying. So on an annual scale, we see most areas of the Mediterranean have a dry. The drying is slightly stronger over the central parts of the Mediterranean, and then also on the western coasts, like the Adriatic coast. The strongest drying so far is in the winter season, and despite the drying, we still have the autumn season or fall season that shows increase in precipitation for the last 30 years. And just to kind of advertise the presentation of my colleague Peter, who will present afterwards, this change in precipitation is mainly due to dynamic changes in the atmosphere. So again, we have here on one hand side a northward shift of the whole circulation system. So basically the circulation system that we have over the northern Africa is moving into the Mediterranean area. And on the other hand, we also have dynamic changes that Peter will talk about. And these are about the persistency of weather systems. So we see also in the observations that we have certain weather patterns that are more persistent, and these weather patterns are inclusive also dryness. Okay, so then let's go to the future projections and how these are spatially distributed over the Mediterranean area. And here I would like to introduce another concept, and this is downscaling, because if you look at what global climate models with a 50 to 200 kilometer scale simulate for the Mediterranean area, you can say that you cannot see any big spatial details. So it's like one country, like Mediterranean here is for this model, like Montenegro is just one width. You cannot have any spatial explicit analysis with this kind of data. And what you need is downscaling. And downscaling is basically a statistical method or also a dynamical method that takes cost-gridded global climate data and tries to refine these data into smaller scales. We distinguish this downscaling into two different types. One type is dynamical downscaling, which is basically taking a global climate model, make some changes to the global climate model that will not anymore simulate the whole globe, but only a small area, but with the same numerical equations. So it's basically the same model, like the global model, but applied to a smaller domain. And since you're simulating only a smaller domain, you can increase the resolution of it. So this is basically the mechanism behind dynamical regional downscaling. And then we have another more easier method that is statistical downscaling, and that basically takes statistical or empirical statistical assumptions and try to relate observations to downscaling. So, or these relationships are usually derived from observations. There are many different methods available for the empirical downscaling. I show here a quite easy method that also involves physical parameterizations. So we know that if we go higher into the mountains, the air gets colder. So you can directly relate orographic height to temperature difference. And you can use these changes to apply to your cost scale model on a finer orographic grid to end up at higher temperature simulations for a more accurate higher detailed temperature observation. But you can also use simply observations and use some statistical model like linear regression, random forest, or like here a neural network to relate the observations on the coarse grid scale to the observations of the finest. So these are the two methods that we use for downscaling: the dynamical downscaling, or short RCMs, for regional climate models, and the empirical statistical downscaling, ESP. And there are certain pros and cons to these methods. So, and these decide basically in which context you use which methods. So if you need a higher resolution, for example, and you are interested in extreme events, you should use dynamical models, because the dynamical models can simulate also novel extremes, while empirical statistical downscaling methods, they rely on observations, so they cannot create new extremes because they are relying on the observations. You are limited to the extremes that are present in the observations. Okay, so then we have applied the downscaling to our global climate models, and now we can have a more accurate representation of the anticipated changes in temperature and precipitation for the Mediterranean area. And here on the left-hand side, we have the real world scenario, so with reduction in emissions for 3 different time spans: 2011, 2030, 2041, 2007, and 2071 to 2100. So it goes into the future here. And on the right-hand side, we have the scenario with the highest possible emissions. And a couple of observations that we can make here is that in general, despite we have applied here downscaling, the temperature increase is quite homogeneous of the Mediterranean area. We have a slight difference between the ocean and the atmosphere, and this has the same reason like we see these differences in on the global scale for the different heat capacities. Then if we compare the green world scenario and the fossil fuel future scenarios, we can see that these two scenarios start to deviate in like 20 years. So right now, we will not see any difference between these two scenarios, but as the fossil fuel storyline accumulates more and more greenhouse gases in the atmosphere, we will start to see changes or difference between the scenarios somewhere between around 2000, the middle of the century. And also the green world scenario, as the emissions from the scenario peak in 2050, we will not see any additional warming under these scenarios until the end of the century. While if we continue to emit greenhouse gas concentrations, we are basically heading for this world here, which shows a temperature increase over the land areas up to 6.7 degrees Celsius for the Mediterranean land. It's interesting to look how this increase in temperature is distributed over the seasons. So here we can see the average temperature increase in red for the high emission scenario and in green for the low emission scenario, how it's changed on average over the different months. And we can see that the peak increase here is in the summer months for the Mediterranean area, and the peak increase goes up to here 8 degrees for the Mediterranean summer. precipitation projections are less certain. So here you can see a lot of hashed areas, so kind of blurred areas, and these areas are areas in the spot that show a statistical not significant change. So either the variability from year to year is too high, or the variability between the models is too high, that you cannot say for certain that this change will happen. So that's why this hash area, and you can basically see that most areas, especially under the green low emission scenario, are statistically not significant, but already this scenario shows a little bit of drying in central areas of the Mediterranean, and this drying will be accelerated under the high emission scenario. And we going here for the late period for the high emission scenario, we are heading towards 320 millimeter per year less precipitation. So that's for the already dry areas over Spain, that's huge. We can also look into the seasonal deviation or the seasonal distribution of this change, and compared to the temperature change, where we see a strong increase in the summer season, we don't see such a strong signal here for precipitation. So the precipitation seems to change homogeneously across the whole. So despite the observations where we see that we had at least an increase of precipitation in the fall, the projections show us that under future high emission scenarios, we will have a decrease in precipitation the whole year round. Okay, so then I would like to go further into detail. So from the Mediterranean area, we go now into the Montenegro changes. And again, here a comparison between the changes in temperature in the upper panel and precipitation in the lower panel. On the left-hand side, the Mediterranean that we just saw. And on the right-hand side, the changes in Montenegro. And what we can basically say here is that Montenegro is quite closely follows the changes that we saw in the Mediterranean area. However, if you go for precipitation, the variability or the uncertainty of these precipitation changes are slightly higher. And this is quite naturally for precipitation. If we go to a higher level, that we really have higher certainty, we go closer into certain region. And for Montenegro, I would finally come to actual climate change impacts. So not just temperature increase, precipitation, but also what other systems are involved or impacted by this climate change. However, I would quickly summarize what temperature change and precipitation change look like for the Mediterranean. On the left-hand side, we have the green scenario. On the right-hand side, we have the high emission scenario. And what you can see here are seasonal temperatures in the upper half and seasonal precipitation changes in the lower half. And what we can say is that we have, under the green emission scenarios, we will have an additional temperature increase in the future until 2100 of 2 degrees to the already observed 2 degrees. So we end up, compared to the history, we end up at a 4-degree world, even with the low emission scenario. However, on the right-hand side, we will end up at 60. So combined with the already observed change, we end up at an 8-degree temperature increase. Precipitation, we have a difference between the different scenarios. So for the green world scenario, we have like winter season and spring season. We is statistically not significant, up to 30 millimeters, and for the high emission scenario, we have a statistically significant precipitation reduction in summer and autumn. So with respect to what we saw for the Mediterranean area for the observations, this increase of precipitation in the fall season is completely done under the projection. Okay, so then I would highlight here some impacts. So what are the direct impacts of this temperature increase and precipitation decrease on some systems for some areas? And here I would like to highlight first the impact on heat waves. And there's an interesting study from Ballester et al. That studied the last 25 years of heat waves in the European area, and they find a quite strong correlation between the summer temperatures and the summer-related heat mortality. So how much people died with respect to a given summer temperature. And as you can see here, this is the line that goes up. So we have the higher the temperature is, the higher the mortality. Now the temperature range we have here is between 19 and 20.5 degrees. So it's a range of 1.5 degree. If we continue with climate change under the high emission scenario, we will end up not at a 1.5 degree change, we will end up at a 6 degree change. So we will end up somewhere up here. So the mortality is anticipated to increase strongly due to climate change that we not do anything about it. And the one aspect that we can look at here, which impacted the heat mortality, is the number of hot days. So the number of days where the maximum daily temperature is above 30 degrees. So if it's the day is so hot, then it puts some pressure on the people. And then we have on the other side, we have on the lower panel, we have tropical nights, which is the number of days that have temperatures above 20 degrees, because we can say that if the temperature is below 20 degrees, we have at least some relaxation in night. So these minimum temperatures are usually night temperatures. So we have high daily temperatures, and we can accommodate to them if we at least have cold night temperatures. However, if we look into or what I show you here is what is the observed. So in the observations, we have fairly low number of hot days. Hot days usually accumulate or center here in the theta plane. And here we have the observations for tropical nights. And then we have in the middle the green world scenarios. And on the right-hand side, we have the high emission scenario. And yeah, here you have the numbers of changes, but the most important facts here is that in general, we see here a bad future for the people. So we have, especially under the high emission scenario, we have nearly all area of Montenegro show heat, hot days. We don't have much areas, only in the mountain peaks where we have days without or seasons without any hot days. And on the other hand, we also have more and more days without any nighttime relaxation. So especially in the theta plains, we have nearly the whole summer season. We have 30 degrees daily maximum temperature, and night temperatures are above 20 degrees. So very hot days and no relaxation in the night. Then another impact is with respect to frost temperatures. And frost temperatures can impact the here in two different ways. One, of course, as I said, winter tourism. So you need frost days, or you need cold days where snow accumulation and snow is needed for winter tourism. And on the other hand, frost can also impact the agriculture. So if you have climate warming and the plant is growing earlier and earlier, or start its development earlier and earlier in the season, you still can have a frost event, and this frost event that can damage your plant and ruin your whole harvest. So frost events can impact also agriculture. And that's why I got here the number of frost days. One on the upper panel for the green ball, on the lower panel for the high emission scenario. And on the left-hand side, it's for the winter season. It's primarily for the winter tourism, because winter tourism takes place in winter season. And on the right-hand side, it's for the spring season, and this is mainly for the agriculture. First, events can damage agriculture. And yeah, what you can see again, first start off with maybe something that is nice for the agriculture perspective. So we have for the spring season in the SSP or in the low emission scenario as well as in the high emission scenario, we have nearly no more frost days in the winter season. So it's warm enough. Even if the plant grows early in the year, we will not have any frost events that can damage the harvest. On the other side, if we go for the winter season, that is quite depressing. So we have less and less areas, even on the mountain peaks, where we have throughout the winter frost days. So even in the peak winter season in January, we will have some days that have daily temperatures above 0 degrees. So the mountain areas of Montenegro will become less and less suitable for winter. Then the impact on agriculture, and here I would like to concentrate on the growing season length. So how much days of the year can be attributed to the places where agriculture can grow plants or crops. And there's a more or less straightforward definition of what is a growing season. The growing season starts with six consecutive days above 5 degrees Celsius, and it ends when the temperature on consecutive days is below 5. So these mark basically a day at the beginning of the year and at the end of the year, and the difference or the length of this period from the growing season length. And what you can see here is the growing season length on the y-axis over the years. And you can see that there, especially for the high emission scenario, so SSP 5, we have a steady increase in the growing season length, which is, at least for the agriculture, quite good because it can lead to conditions where we even have multiple harvest years. So you can plant again in summer or in autumn and still have the harvest this year, because of the higher growing season, longer growing season. Okay, and one impact that I would like to touch that was also partly touched in the previous presentations, and I would also like to touch tomorrow in the presentation, and this is the impact on viticulture. And for viticulture, to get a general idea in which region you can plant which variety of wine. There is a indicator that is called the Hugon index. This one. This is some complicated or not so complicated formula summing up the temperature over the year. And this gives you a specific index or a specific number, and this number can tell you or can be related to a specific variety. So if you have warm conditions, this sum over the year will be quite high, and you have accumulated high amount of temperature. If you have low temperature, then this accumulation will be quite low, so you have low. And at the end, you can relate these numbers to specific varieties. For example, the lower numbers, around 1,000, 1,500, are usually related to wide varieties, and the higher numbers are usually related to red wines. And here, for example, the Granats, that is the famous variety in Montenegro, has Hugon values around 3,000. And what we can do now is we can calculate the Hugon index based on the simulated temperatures, and then see how on one hand side the area where you can grow certain varieties of wine shift, and also you get new areas where you can grow maybe in future one of the warmer conditions. And this is what is depicted here. So right now, the conditions today are depicted here in the top. And you can see that most wine regions or the most suitable areas for growing wine are the cedar plains, and also the areas along the coast, which are actually the areas where most of the wine is growing. If we go to future climate projections, here again on the top panel, 3 different periods under the green scenario and 3 different periods under 2100 for the high emission scenario. We can see that especially for the high emission scenario, we have more and more areas where we can grow wine. So where we have Hugon indices above 10,000, and we also have a shift of areas that are previously more suitable for white wines towards areas that are more suitable for white wines. So this is in general can be attributed as a pro argument of climate change, where we have more areas that can be used for wine. However, as we have seen from the presentation of Daniel and Justina, there's much more behind it. So it's not just you cannot just simply use these temperature sums and then decide how you adapt to climate change. But climate change will also have more detailed impacts on the growing and the phenology of the wine. And this is one aspect that I would like to touch tomorrow in the presentation, where we go more into detail on the wine phenology and how the wine phenology changes under future climate conditions. So this is basically more starting point for the presentation tomorrow. So in summary, we have seen that the Mediterranean area already has observed significant temperature increase of 2 degrees and a strong precipitation decrease, especially in the summer season. Going to the future, this reduction in annual average precipitation will continue. We will have, even in the autumn season, we will have a decrease in precipitation, and the temperature increase will rise by an additional 6 to 7 degrees Celsius. Montenegro, in detail, will face under the high emission scenario temperature increase of 6 degrees and the precipitation decrease of 230 per year. The Cedar Plain is, for most pictures, the most affected area with respect to climate change. So we have, for example, for the number of hot days and tropical nights, you can see that for the Cedar Plain, you will basically have the whole summer months only hot days and tropical nights. So hot days and no relaxation in the night. On the other hand, we have some positive news on climate change. We have an increased agricultural area. We will have an increased growing season. However, always providing that we have enough water also for growing. And yeah, we have seen that we have, at least in principle, a better wine production, more areas where we can grow red wines, and more areas where we can grow wines in general. However, this is just, as I said, the starting point, and we will continue on this impact of climate change on wine productivity tomorrow in the presentation knowledge. Okay, and that's all I would like to say. If we have some time, maybe there are some questions. So, yes.
About here, my question is, how long does it actually take to for someone to become familiar with climate data and to start working with real climate data? I've been a project for almost 3 years, and it's still a challenge for me to understand everything about it. And in fact, how deeply do we have to understand climate to work with such a?
That's a difficult question. For me as a researcher, I would say it will never end. So there are always some certain aspects and details that you need to learn. It's really, for me, you basically pick up a specific area of research, like how does climate change impact viticulture development? And then you start there building up some expertise. And then on a certain level, you change maybe to how does climate change impact the distribution of pests? And then you basically learn completely new things from scratch. So always, I mean, you can have like after 3 years of studying the relationships between climate change and wine, you maybe have all the aspects considered with regard, but if you change the topic, that you learn completely new stuff. And yeah, I mean, it's an ongoing research. So even though we know that, for example, the ocean circulation is changing, there is a huge ongoing research, how it changed, what is the time scale of the change, how to measure specific aspects of this change. So it's even the experts on this area do not know everything. So this is ongoing research.
Question about why is the discuss about
Yeah. Any more questions? Okay. Are there online any questions or?
I don't think so. Let's check. See.
hearing from me? Not hearing. Let me just stop sharing. No questions. No, not for now. Is there any questions?
Are there any questions from the online participants? We can move forward, and then if we have other questions, we can ask later. Okay.
Okay.
Thank you, Teresa. As Chris mentioned before, our next presenter is also from Peter Faulkner, and the presentation too wet, too hot, too dry, weather persisting in Europe.
Okay, perfect. So I think now I can start, hopefully. So yeah, my name is Peter Hoffmann from Potsdam Institute for Climate Impact Research. I'm a meteorologist by training. And since 2012, I'm in the working group of hydroclimatic risk at the Potsdam Institute. And in my research, I'm focusing on climate diagnostic, and I'm very interested into weather phenomena and how they change in the context of climate change. And here you can see the title of my presentation. What is the rule of the weather persistence in Europe? Because we see much more frequent periods that are too dry, too wet, or too hot. And I will try to look into the mechanism behind. And at first, let me give you a short outline of my presentation. First topic will be about weather variability and about meteorological phenomena. And then the second topic, I will try to give local extreme weather events a large-scale context, because extreme events have a driver, a large-scale driver, and I will give you what pattern are the main trigger for extreme weather events on a local scale. And then I will introduce you into weather type classification and existing weather type classification for Europe, and I will give you one possible application for that. And then, how will the weather variability will change in the context of climate change? And one main element of the weather variability is the weather persistence. And the question how the weather persistence has already changed in the observed climate. And this will be the next point, the weather persistence in Europe, and then how can we identify weather types in climate scenarios, because these patterns are very relevant for extremes or for the seasonal variability of rainfall, and that's why we have to better understand climate scenarios in the context of the weather variability. And at the end, I will finish with a case study from a last project in Jordan, where we focusing on extreme rainfall. Jordan is a country in the eastern Mediterranean or in the Near East region, and I will come later to this point. So the first topic of the seven is the weather variability and the meteorological phenomena behind. Let me start with a view on the temperature variability or weather variability of the last 2 years for a climate station in Central Europe. What you can see are temperature anomalies compared to a mean seasonal cycle from the 1960s to 1980s, and the red color represent the positive anomalies, which means that periods that are too warm or too long, too warm, and you can also see during the last 2 years there is also some event or some episodes that were too cold. But if you average over the last 2 years the anomalies, you're resulting a value that is 2.8 degrees warmer compared to the reference period 1961 to 1990, which means this is not surprising because the temperature over continents, over Europe, are amplified in the warming rate, and that's why we can see that climate change is ongoing, and the last 2 years were exceptional warm compared to the previous periods. And if you compare to weather or climate conditions, one in Podgorica and the other one in Berlin, for example, you can see, if you look at the temperature variations, you can see that Berlin, the maximum temperature in summer is in the order of 30 degrees, but in the Mediterranean area here in Podgorica, the temperature are much higher, about 5 or up to 8 degrees warmer compared to the conditions in Berlin. But you can also see a difference between the Central European condition and the Mediterranean, that in Central Europe, you have almost in all seasons rainfall. But in the Mediterranean area, you have seen that the summers are dry and the main rain events occur in the transition from summer to winter or in the whole winter season. No, but the main driver for the temperature variability in Europe are the large-scale transport of air masses across different geographical regions, and we would distinguish between 2 different main flow patterns. The one is the zonal flow. You can see a gradient between north and south conditions, which result in a strong westerly flow coming from the North Atlantic to the east. And the north part is normally colder compared to the southern part. But these conditions can be disturbed by meridional weather patterns, so-called high pressure system over Central Europe. Then the flow pattern shows a southward component of a transport, which means that warm temperature can reach high latitude, or cold temperature condition can reach low latitude. During these meridional weather patterns, you have a strong transport over latitude. There's a strong transport from the warming to the cold areas. This is the most dominant weather pattern in Europe. It's influence from the North Atlantic with a strong westerly flow. This is characterized that low pressure system very fast moving from west to east, and also the associated rainfall patterns very fast propagate from the North Atlantic to the east. And this weather pattern is more or less a very moderate. There are no extremes are likely during this kind of flow pattern. If you have a meridional circulation condition, like a high pressure, as already mentioned it before, we have a strong meridional transport. Here we have a high blocking over Central Europe, which means that low pressure systems are blocked. They cannot propagate from west to east. They move northward, which means that during this weather pattern, the Central Europe is mostly dry and sunny, and in summer we have a heat wave under this condition. And if you look into the vertical transport, the air masses are downward. If you look into the reverse condition, we have a trough over Central Europe. Then we also have a kind of blocking that low pressure system cannot really move to west or to east. They are like in a trough fixed, and they very slowly move, and there is a high persistence of low pressure systems over an area. And if a low pressure system persists over longer time than expected, then it can also link to extreme rainfall. And also a very prominent pattern is the so-called omega-like circulation pattern, where we have low pressure systems on the west side of the omega and a high pressure blocking system in a high latitude region, and this circulation pattern can be very persistent, and which means that extremes or heavy rainfall on the one hand and extreme heat or extreme drought condition can persist at the same time at different places. And such a blocking phenomena can be identified by a so-called blocking index. The blocking index is calculated by the meridional pressure gradient. And if you have high pressure systems in high latitude and low pressure systems in low latitudes, then you have a blocking situation, which is called high over low. And during the last couple of weeks, or even since March, we had a high blocking frequency around 0 in the longitude range of the British island, which was very likely associated with the drought condition in the western parts of the European region. So these patterns are very prominent, and these patterns are also linked with surface temperature and rainfall conditions. Here you can see on the left-hand side a so-called high pressure system with a anticyclonic situation is often associated with positive temperature anomalies over the western parts of Europe. And on the right-hand side, you see a trough-like pattern or a low pressure system over Central Europe. This pattern is often associated with permanent rainfall in the Central European region. Which means that if you have if you only see the circulation pattern, we know from experience that, okay, this pattern is often associated with rainfall, and the other is often associated with dry condition or with heat. The shape of the circulation pattern alone gives you information about expected local weather condition. The next point I will go to more to extremes, and I will show you what is the large-scale context of specific extremes in recent years. On every local extremes has a large-scale context. It can be a local heavy rainfall event. It can be a high temperature. It can be also a cold wave. But the main driver for this local extreme is the large-scale context. And the large-scale context is more or less the flow condition. The flow conditions are the main driver for the local extreme. As I already mentioned, the extreme or the can have a different scale. It can be a local thunderstorm. Thunderstorms are on a local, a very small scale, having characteristical time scale of several hours and a few kilometers. And the larger scale phenomena like heat waves or river floods, they have a larger extent, 100,000 kilometer extent, and a much longer characteristical time scale. And here I want to give you one practical example. I developed a web application that will show you the large-scale context of high temperature, for example, in Central Europe. In the URL, you can see 4 parameters. The first parameter is the meteorological variable. The 2 other parameters are the longitude and latitude, and the last parameter is the percentile. Based on this local data, we filter atmospheric fields to see how the pattern looks like that favor high temperature in Central Europe or high precipitation or very high precipitation events in Montenegro. Here I will start an example, starting with the high temperature condition in Central Europe. The red dot marks the location of interest, the point of interest, and the large scale context show the pattern that is often associated with high temperature in Central Europe. The next one, we go to high precipitation values in Central Europe at the same location. And here we can see for this location a trough-like pattern, as already mentioned. Trough-like patterns are more associated with wet conditions and And then let's have a look at the heavy or very high precipitation in Montenegro. How looks the large-scale context? You can see a trough-like pattern down to the Mediterranean area. In this context, if you see, for example, in weather forecast or climate projection such a pattern, then we can see, okay, this pattern is often associated with extreme rainfall condition in the eastern Mediterranean area, for example. For the last years, we have seen several extreme rainfall events. The first one was the event in July 21, the Ahrtal flood in Germany. Another one was extreme rainfall event with increase with 1,000 millimeter per day. It was an extremely unusual event where the annual rainfall rained down within only 1 day. And another example is Valencia in last year in November. And also here it's interesting to see what are the main atmospheric circulation patterns that trigger such unusual extreme events. And here's the example for the Germany case. The Ahrtal flood is a low pressure system over southern or central Europe. You can see that moisture from the Mediterranean is moved northward, and this can trigger extreme rainfall events in the area in the northern part of the Alp. The other case is the extreme rainfall event in Greece. We had a strong meridional flow from north to south, and during beginning of September in 23, the SST, the sea surface temperature of the Mediterranean area was extremely high. And this combination of cold air from the north over high SST temperature can trigger such convective rainfall events. And in combination, this can also trigger also some medicants over the eastern part of the Mediterranean area. And the last event was this Valencia event. We had a cutoff low, very cold temperature in the upper altitude, and also high temperature in the lower level. And this combination is also can trigger very intensive rainfall events. And in combination with the persistence, we have a persistent low pressure system that don't move forward, that persist over days at the same time, and the rainfall area rain down always at the same location. So the critical circulation pattern is the one. The other factor is the temperature rise. The temperature rise, the warmer atmosphere can save more water vapor. And in the recent report by the Copernicus, they reported that the water vapor has increased by about 70% since 1990, and during this time, the temperature has increased by almost 1 degree. That means that 1 degree temperature increase has a higher water vapor content by about 7%. Which means that on the one hand, we have more moisture in the atmosphere, but then we need a critical circulation pattern that can rain out over a critical complex topography, for example, and then such events can trigger flash floods, for instance. And on the one hand, we have a higher frequency to drought conditions on the one hand, and a higher potential of extreme rainfall. For Europe, we have a catalog, a historical catalog of so-called circulation patterns. This catalog goes back to the 60s, and every day is assigned to one of these circulation patterns. And in total, it is the number is 30 different weather patterns explain the weather variability over Europe. The most frequent one is given in the upper row. On the left, you can see the westerly flow, the most dominant one. It explains about 15% of the weather variability. And then you go left and you see some patterns. They have a trough-like circulation pattern where low pressure system don't move from west to east, but from north to south over the Mediterranean area, and also some pattern like a high pressure system over Central Europe. Then you have patterns like a southwest flow pattern is often associated with heat extremes, and also some specific patterns like an omega pattern. You can see that the shape of the circulation is like a omega, or low pressure system over Central Europe, and so on. And every pattern is locally associated with some characteristic weather conditions. The westerly pattern is more or less very unstable, associated with unstable weather condition. The trough over Central Europe more, it's a wet weather type, and high pressure system over Central Europe weather type, often associated with heat or drought condition. And here you can see it in more detail, the different weather patterns on the y-axis and the different months. And every weather pattern has locally a certain characteristic in terms of temperature or in terms of precipitation. Here's an example for Eastern Germany, Potsdam. You can see that south anticyclonic weather condition is the hottest one in summer, and the west cyclonic situation is the most moderate in terms of temperature, and the most wettest weather type is low pressure system over Central Europe in summer season, and the west cyclonic is almost wet in all months. And you can also see which weather patterns are more associated with dry conditions. And this matrix strongly depends on the location. The patterns are defined for the whole Europe, but the local representation depends on the local meteorological condition. And for example, for extreme events such a river flood in 2002 over the Danube river catchment, you can see very persistent weather patterns, not over days up to week, that one and the same critical weather pattern persists over almost 1 week. And the same is for the heat condition in September 23. Almost one and the same weather pattern persists over 2 or 3 weeks. And this the longer one and the same weather pattern persists, then the stronger can be the impact on human, but also on agriculture. The next one, what has changed during the last decades? Climate change, on the one hand, is simply a shift in the distribution. You can see the curve, the distribution, the temperature variability has shifted by about 1 degree comparing the 60s with the present period, but the weather variability has not shifted. The weather variability has a much stronger spread in both direction, one into the warm end of the distribution, but also on the cold end, which means that under climate change, the weather variability becomes more extreme in certain cases. And what's the reason behind? One reason is that as Christoph already mentioned it, that the warming is not evenly distributed. The continents and also the Arctic, we see an amplified warming during the last decades, and this differential heating of the world surface has also an effect on the circulation. The stronger the Arctic amplification, the stronger the amplified warming of the continents compared to the ocean, the more likely the circulation moves from a more zonal flow pattern to a more meridional flow pattern. And a more meridional flow pattern is often associated with a transport of temperature across different latitudes. And we also see a long-term change in the patterns, in the circulation pattern, that in recent years we see that the westerly wind patterns become less frequent. We see a decrease in the zonal flow pattern. The influence from the North Atlantic slowed down. On the other hand, we see more meridional circulation pattern, 12 over Central Europe or Southwest cyclonic. And these patterns are often associated with extremes, not only in Central Europe, but also in the Mediterranean area. And also the persistence has increased. On the one hand, we see this slide or this graph show the distribution of weather persistence for each month. The blue curve shows the distribution in the past, and the red one in the present period, and especially in April, June, and July, we see an increase in the weather persistence from more or less from 4 days to about 6 or 7 days, which means that, for example, spring conditions become more persistent, but also summer conditions. Which role plays the weather persistence? In 2021, we published a study which focusing on the analysis of weather persistence on a larger scale. In this study, we analyzed or we compare atmospheric fields using an image comparison program. We compare day-to-day images in terms of the similarity. And here on the right-hand side, you can see an example that in case of July 2006, it was a very persistent weather conditions where the contour lines, the pressure contour lines, from day to day show a very slow change over time. And with this image comparison program, we compare the day-to-day similarities. And we screen, using this approach, a global data set and found that especially in Northern Hemisphere summer, we see an increase in the atmosphere similarity, or in other words, an increase in the weather persistence. the weather persistence has increased in a band from the North Atlantic over Europe to Siberia. And this increase in the weather persistence, we correlated it with temperature and precipitation. And for Europe, we found that the temperature is positive, or the weather persistence is positive correlated to temperature, which means that persistent summer are hot summers. And on the other hand, we also correlated the persistence with temperature, with precipitation values, and found the persistence is negative correlated with precipitation over Europe, which means that persistent summers sind on the one hand hot summers, but also dry summers in most parts of Europe, especially in the southern, but also in the northern part of Europe. And then how can we identify these patterns in climate scenarios? For this, we apply a random forest approach, where this random forest approach is trained by data, and for the training period we have atmospheric fields on the one hand, and the classified weather types. And for this training period, we train the rules between the atmospheric fields and the weather types, and then in the prediction, we take new unclassified atmospheric fields, apply this training to predict the weather types in, for example, in climate models. And then we can compare the observed variability in our observations on the one hand, and compare the variability in climate simulations. And what we can see on the one hand, that the westerly wind patterns become less frequent in the observation data, but in the simulation data here, for example, there is no clear trend or negative trend visible. And so we can go through all of these different weather patterns that are also linked to extreme events, such as drought over century or some other critical weather types. And then another example is the application to numerical weather forecast. And here we can also identify the simulated or the predicted weather patterns to these circulation types. And here you can see for the current forecast that we see, okay, this pattern is identified as a westerly wind pattern. And then the next 3 days we get a southwest component of the circulation. And this can be done for the whole ensemble of forecasts. And we can see on the right-hand side a chart where we can see during the past days, our weather was highly explained by a westerly wind pattern. And next days, we expect a heat wave for about 3 or 2 days. And this can be easily evaluated by using this complexity reduction, using this approach. And the big challenge is if you compare observed trends in rainfall patterns, we can see areas where the total rainfall goes down, the trend is downward directed, and we have areas where the trend is positive. But in climate ensemble simulation, we cannot see these patterns. And we hopefully that these patterns, the analysis of circulation pattern or rainfall patterns, will give more insight into the weather variability in climate model simulations. And then finally, I would like to highlight one finished project during the last 3 years. We had a project in Jordan with a focus on extreme rainfall. Jordan is located in the Eastern Mediterranean area, in the Near East region. It's dominated by an arid climate. It's very dry. It belongs to one of the driest countries worldwide. But in winter season, so our focus areas on the one hand was the city of Amman. It's located in the northwest of Jordan, and the other focus region was Petra. It's a rocket city where many tourists visiting Petra every day. And we have a problem with extreme rainfall, because extreme rainfall in that area can trigger flash flood in a urban area on the one hand, or flash flood in a wadi system like Petra. And such flash floods are very dangerous because the early warning is very limited. And here you can see the seasonal cycle of rainfall in Jordan. There's almost no rainfall in Jordan during the summer months. And in the winter season, or starting from October until May, we can see from time to time rainfall events in the order of up to 100 millimeter per day. And we also analyzed the main context for extreme rainfall events in this area. We studied the large-scale patterns. On the one hand, then we developed some early warning tools. We analyzed long-term climate scenarios, and we also drive hydrological models with these rainfall scenarios to see how will change the flooded area in urban areas like Amman, but also in wadi systems like Petra. Yeah, and then my take-home message or summary is that there is a causal linkage between large-scale weather phenomena and local extremes or local weather conditions, and it's important to consider both. And there are some dynamical change. These are the main source for projecting future climate and future rainfall scenarios beyond the mean temperature rise. Because this is compared to that easy to project the temperature rise, but the rainfall patterns are more linked to the circulation conditions. And then we also analyzed some future scenarios and found, depends on the region, also some discrepancies between the real world and the modeled world, especially in terms of drought conditions. And then we have to stronger learn from historical data about the phenomena to better understand the real climate or the regional climate scenarios in future. Then I would like to thank you for your attention, and thank you.
there any question? I don't think we have online, just check in. Okay, thank you, Petra. And the first day of the summer school, we will prepare presentation by Carlos from remote sensing innovations for monitoring vine growth from drone-based analysis to our applications. Thank you. So, I will change your screen here. Hi, Adam. You're not hearing me yet. Please check your microphone is working.
Hello? Hello, everyone?
I can hear you, but it's a little bit low. Could you please check in the louder? Yeah.
I'm sorry, can you hear me?
Yeah, now it's better. Thank you.
Okay, and can you also see my screen?
Yeah, you're seeing your screen.
Okay, nice, so I can start. Okay, so good afternoon, everyone. My name is Riccardo Rossi. I'm from the University of Florence. The department is the Agri department. And this afternoon, I will show you some innovative technologies that we can use for monitoring the vine growth directly in the field, starting from the drone base up to the SAR application. So let's start by introducing myself. I've got a bachelor degree in agricultural sciences and a master degree in agricultural sciences and technologies that I have obtained at the University of Florence, as well as a postdoctoral in agricultural and environmental sciences, on which I have focused my research activity on image-based plant phenotyping, which will be a main focus of this presentation. Currently, I've got a postdoc position at the University of Florence at the Agri department, and I'm involved in several projects from image-based phenotyping up to the monitoring of plants directly in the field, like the vineyard. So I've divided this presentation in 4 main sections. The first one is the introduction section about the topic that we will analyze in detail, like the UAV application and the SAR application usage for the monitoring of the vine growth directly in the field, which represent the second and third section. And lastly, I have included some practical application like the three-dimensional modeling of a vineyard, starting from the images acquired by a drone, and then the pre-processing steps that we have to conduct, we have to carry out for the satellite image, like the SAR images. So let's start with introduction. So all of us know that European countries are the main leading countries with respect to the wine production worldwide. But you also know that the climate change is impacting the viticulture and wine production at the global scale, but also at the European scale. But we have to remind that exists a trade-off between the impact of the greenhouse gases emission on the viticulture and wine production and the impact of the wine industry to the greenhouse gases emission. So it's important to adopt a series of strategies which refer to the life cycle assessment of the wine sector. Oh. I think somewhere I've got the audio. Could I continue? because I'm listening some noise.
Це шутра. Biće dana. Jedna danas, druga šutra, treća prekšutra.
Sorry, could I continue? Some noise.
Moram da tamo da idem do Arune, pa je tu onaj bankomat. Da. Onda,
Okay, could I continue? Yeah. Okay, so this kind of approaches involved several actors in the wine production, from the farmers to the governmental institutions up to the consumers, the final consumer. And the carbon footprint is the most suitable SCA-based indicator for assessing the greenhouse gases emission which result from the wine industry. But we know that it's complex to evaluate the carbon footprint of all the entire wine value chain because it's composed by different steps, which start from the growth of the plants in the field up to the final consumption by the consumers. But in our case, obviously, we are interested in the pre-production section. So in the section we refer to the growing of the plants in the field, and we are interested in monitoring the growth of the plants. And to do this, we can assess, we can evaluate what we are able to observe in the field. So the cultivation of the plants, the pest control, the pruning of the plants, and the everything at the end. So how can we monitor what we are able to observe in the field? By evaluate and assess the phenotype of the plants. So the phenotypes was characterized for the first time by William Johnson, which say that all types of organisms can be distinguished by direct inspection or with finer methods of measurement or description. So more easily, the phenotypes are the observable characteristics of an organism. So the characteristics of a plant, of an animal, of humans, and so on. In our case, obviously, we are interested in the observable traits, observable characteristics of a plant. So it's important to know that the phenotype is the expression of the interaction between the genotype of a plant and the environment on which the plant grows. So in the first case, you can see I've reported an image of a flamingo because it's a typical example of how the phenotype is influenced by the genotype, because you know that this kind of bird usually hits a particular species of fish, which is full of carotenoids, and it gives the color of the feathers of the flamingo, which naturally are white. Instead, due to the genotype, obviously they show pink. So in the second case, obviously, we have the effect of the environment on the phenotypes. In this case, an example could be the colors, the morphology of the plants, which we know are directly influenced by the environment on which they grow. So, in conclusion, the plants with the same genotype can have different phenotypes depending on the environmental and lifestyle factors. An example could be the two different plants which grow in two different environments. So the same plant grow in different environments at the end of its cycle, they will have different characteristics like the color of the leaves, which could be yellow if the plants grow on a stressful environment, or green if the same plant grow on a optimal environment. So that's the influence of the environment on the aspect of the plant that we can observe of the plant, which is the phenotype. The expression of a specific quantitative trait depends on the QTL, which has the quantitative trait lodges, which are segment of the DNA of the plants, which contribute to the expression of the quantitative traits of the plants. And it is important to differentiate between qualitative and quantitative traits. The first one are discrete and easy to measure values, while the other one are continuous and difficult to measure values. Here I have reported some examples. So you can see in blue the quantitative traits, in red the qualitative traits. So the canopy biomass, the plant height are quantitative traits because they are difficult to measure, because you need to use I don't know, some metric rulers or some balance for the acquiring the weight of the canopy biomass and so on. So they are more difficult to evaluate with respect to the fruit shape, bunches colors, because it's simple to see if a bunch is green or if a branch is I don't know, violet or black on the maturity stage. So that's important to consider these differences. It's important because the plant phenotyping is the ensemble of techniques, methods, which quantify the plant's phenotype. So basically the plant phenotypes aims to quantitatively analyze the aspect of the plants which could be translated in the phenotypic traits. Usually this kind of analysis is carried out by using manual surveys, which are error prone because the human biases. They are time consuming, especially if they are repeated over the time and over multiple samples, and for this reason are also expensive. Another drawback of these kind of surveys are that if they are destructive, they are not repeatable over time in the same plant, so we cannot monitor a trait or a plant of interest during the growing season, for example, because obviously we have destroyed the plant. So to solve this drawback, to solve these criticalities, we can use the photogrammetry science, which is the science and technology of obtaining reliable information about physical objects and the environment through the process of recording, measuring, and interpreting images. So the photogrammetry is basically composed of 3 steps. The first one is the acquisition of the images. The second one is the measuring and assessing of this kind of image. And the final step is the interpretation of the image in order to extract useful information about the plant phenotype. So in general, the image-based surveys are repeatable over time on the same plant because they are usually based on non-destructive image acquisition, and for this reason are more accurate and rapid with respect to the manual surveys, and with respect to the sensor and technology that we can use to obtain the image, they are inexpensive and could be obtain recursive information on the same plant or on the same organ. So the photogrammetry is it could be divided in 2 different approaches: the proximal sensing and the remote sensing approaches. Going from the full scale up to the mid scale, which is the spatial resolution of the information that we want to acquire. Obviously, exists a trade-off between the time and accuracy. So if we use remote sensing technology, we gain the time. So this kind of technologies are less time consuming with respect to the proximal sensing technologies, but the spatial resolution is less. So the approaches that I will show you in this presentation refer to the remote sensing approaches, so drone-based and satellite-based approaches. So for inside the remote sensing approaches, the aerial photogrammetries, it refers to photographs of the object that can be acquired from an elevated position. So the sensor that acquired the image is not supported by ground-based tractor, as for example the ground-based phenotyping platform that refers to the proximal sensing technologies. So the advantages that can we obtain by using the aerial photogrammetries are listed in the slide. So we can monitor large areas like field areas, which are not possible by using handheld instruments, which refer to the proximal sensing approaches. We can obtain a large amount of information in a short period of time, and sometimes we can obtain this kind of information for free. We can refer to the satellite images, like for example the Sentinel image that can be downloaded for free from the website. On the other hand, also in this case, we have to consider some drawbacks, like the dependency of the information that we can acquire by using these technologies on the type of crop, and in particular on the morphology of the crops. Also, the influence of the environmental condition, because we know that, for example, during windy days or rainy days, we cannot use UAVs, for example, for obtaining information about the crop. And then we also to consider the technical requirements like the cost and the airspace regulation, because, for example, we cannot fly with our drones near the military zones. So now I will show you some imaging approaches that we have used for the experimentation that I will show you after the introduction section. The first one is the RGB imaging. So it's the more common image-based approach. So the acquisition of red, green, and blue images, which are referred to the visible range of the spectrum. And it's important to underline that inside a RGB image, we have two important information. The first one is the size of the pixel, which defines the spatial resolution of the image. So the smallest the pixel, the highest the spatial resolution of the image. The second kind of information that is stored inside an RGB image is the intensity of the red, green, and blue channel. So per each pixel, we have these two important information: the dimension of the pixel and the intensity of the three channels that compose the image. And we can elaborate, we can process these images in order to obtain the phenotypic information of the plants, so the phenotypic traits that we are interested in. The most simple approach is by using a single view two-dimensional image for extracting simple information about the plants, so non-complex information about the canopy architectures, like for example the plant height or the leaf area of the plants. But obviously they are limited in their usage for the representation of the real morphology of the real architecture of a canopy. So the second option is to merge the information that derives from multiple view two-dimensional image sequences of the same plant. And a classical example is the fusion of the same traits that can be obtained from a side view image and the traits that can be obtained by a top view image. For example, the projected plant area merge the plant area extract from a side view image and the plant area extract from the top view image of the same plants. And this kind of operation reprojects this kind of trait in a space which could be more similar to a three-dimensional space. The third option is the more accurate option for the reproduction of the three-dimensional architecture of the plants is the triangulation. So also in this case, we can merge and fuse the information derived from a series of images but in this case, we have to have two or more two-dimensional images. So a practical approach to obtain a three-dimensional reconstruction of an object or of a plant, in our case, by using a sequence of two-dimensional images is the multi-view stereo vision, which is basically based on the acquisition of sequences of image on the same plant, of the same target, from different viewpoints. And after this kind of acquisition, we can use the structure transformation approach for automatically estimate the intrinsic and extrinsic parameters of the camera, like the distortion, the pixel size, the focal length, the position of the camera from which we have acquired images. And this kind of information can be obtained automatically and allow to reconstruct the real three-dimensional architecture of the plants, as you can see on the example in the image. So here I have reported a classical example of this workflow. So we have the first step, the raw image data, which are the two-dimensional images that we have acquired on a specific target, on a specific plant. And it's important that consequent image have a common area on which we have the same information, the same portion of the plants which is included in the image. That's important because in the next step we have to identify the common points between consequent images, which are called tie points, in order to obtain a sparse point cloud that, as you can see on the slide, is a reconstruction, three-dimensional reconstruction of the object, but it's composed by a low number of points, which are exclusively the tie points, so the common point between the different images. After that, we can apply another step, another process for the obtainment of the dense point cloud, which basically intensify and increase the number of points of the sparse point cloud by a pixel-to-pixel analysis in order to reconstruct a more feasible representation in the three-dimensional space of the plants or of the object. So the second image-based approach that I would like to show you is the multispectral imaging, which captures data at specific wavelength bands across the electromagnetic spectrum. So typically, this kind of information includes the visible image, so the RGB channel, but also the non-visible bands, which are referred to the near-infrared and radiation bands. So in this case, we have more information storage at the pixel level, which are represented by the different bands which we have acquired by using our sensor. So each pixel is composed by different layers of information, which are the bands on which we have acquired by using the multispectral sensor. And this kind of technology is very, very useful for a series of applications for the monitoring of the plant status, like, for example, the early detection of stress, because as you can see in the image of the slide, the difference in the response in the near-infrared band is greater with respect to the response of the red, green, blue, so the visible bands, if we compare the dead leaf and a healthy leaf. So we can use this kind of information for an early detection of an abiotic or abiotic stress. But also we can merge the information acquired at the specific bands in vegetation indices for the obtainment of more complex information about the plants, like also in this case the health status of the plants, the density, the greenness of the canopy, and so on. So lastly, I would like to introduce the radio detection and ranging imaging, which is also called radar, which is an active system instead of the passive system that we have seen before. We have the electromagnetic radiation, which derive from the sensor of the radar and hit the target, the object that we are interested to monitor. So this kind of radiation propagates in the atmosphere, in the vacuum, at the speed of the light, and is characterized by an oscillating electric and magnetic field. I'm not an expert of radar, so I will go faster. The electromagnetic waves are characterized by a wavelength and a frequency. Sorry. As you can see in the figure, which are inversely proportional. So that's the spectrum and the electromagnetic length. The length of the electromagnetic waves, which we are talking about. And so radar are systems which are equipped with an antenna that operates as a transmitter and a signal receiver. For this reason, this kind of technology is an active system. And the signal the signal emitted by the antenna is reflected by the target on the surface. We can obtain several information about the target and about the surface. To convert this kind of signal, which is an energy signal, to an imagery, we can refer to the intensity of the reflected signal, which is stored inside the pixel of the image. So in this way, the pixel value is proportional to the intensity of the reflected signal, and we can compose the image. So all spaceborne radar systems are SAR, so synthetic aperture radar, which have a final resolution and most importantly are independent of distance and cloud. So we can obtain information also during cloudy days, also during rainy days, because the specificity of this kind of technology. The orientation of the electrical field gives us the polarization of the signal, which is divided into H and V, so horizontal and vertical, transmit and receive, and we can merge, we can fuse these two kind of information to obtain important traits about the vegetation. So the example is the volume scattering, or in general the scattering mechanism, which define how the signal interacts with the object. And so by assessing this kind of signal, we can apply the SAR technology to estimate the biomass, to assess the canopy structure of our plants, have information about the soil moisture, the phenological stage of the plants, and so on. So after this introduction section, we can switch to the application, which I will show you some results of the application of these kind of technologies on a vineyard, which is located in the Chianti district. So we have a field of about 4 hectares with Sangiovese variety, and with the distance between the plants of 90 centimeters and between the rows of 2 meters. You can see the area of the vineyard on which we have acquired several information during 2 growing seasons. In particular, you can see 10 boxes inside we have collect all the information that we have used for the obtainment of the result that I'm going to show you. So for a briefly recap, we obtain several information inside these pixels, like the environmental measurement by using soil moisture probes and other sensors for the air humidity and temperature. Then we also collect ground measurement at plant scale, also for the vines and for the grass in the interrow. And then we have collected the data by using a drone at 3 time points during the season. So at the flowering, at the fruit setting, and at the harvest time. After that, at the end of the growing season, we also have collected the pruning and the fruit's weight at each plant level. And also we have collected an FAPAR, the fraction of photosynthetically active radiation. The image that we have acquired using the drone had a resolution of 2.6 centimeters, and the drone was equipped by a multispectral camera. So the first application was the usage of UAV data for the estimation of the FPAR. To do this, we have defoliate 10 plants by consequently defoliate in 5 steps the plants, and then we acquire some images by using a simple hand-handled RGB camera of the shadow of the plants, and also by acquiring the same images by using the drone. And for the observer measurement, we use the cheptometer to directly detect the real FPAR in proximity of the plant. So that's a very easy application, but the results are interesting because by elaborate this kind of image, so both the proximal image and the UAV image, we have obtained very, very great accuracy in the estimation of the FAPAR, so we can conclude that we can just obtain some UAV images of the field, extract automatically the shade of the shadow of these plants, and estimate an important parameter like the fraction of photosynthetically absorbed active radiation by the plants. So the second approach aimed to develop an UAV-based semi-automatic methodology to optimize the canopy management for starting from the 2-dimensional images of the UAV. So in this case, we have calculated several indices that are representative for the balance between the vegetative and the productive sides of the plant. So we have calculated the Roberts index, the growth balance index, and the renovate dry matter index. After the acquisition of the images from the drone, we have implemented a semi-automatic 2-dimensional image-based processing approach by using the QGIS and the RStudio software. The first step of this kind of methods include the identification of the starting and of the ending point of each row, and this was made manually. That's why we call this kind of approach semi-automatic, because it's not fully automatic. So after the identification of the single rows, we have identified theoretically the position of each plant, which in the slide is represented by the dots, the red dots. So by considering the distance of the between the plants, which we know, and after that we also consider a box, so a buffer box around each dots in order to consider the area on which if the individual plants were growing. So after that, we remove the information about the soil and the grass by subtracting the digital terrain model from the digital surface model, and the result is the images on the right. So the white pixels are referred to the plant pixels. So in this way, we remove the information about the soil and the grassland. And after that, we implemented an automatic algorithm for the detection of the individual plants, but also of the eventual voids inside the field. So in this way, we were able to extract specific information, specific phenotypic information about the plants, like, for example, the plant area, and a lot of vegetation indexes, because I remind you, we use a multispectral camera. So we extracted the vegetation indexes that are listed in the slide. And we compare these two kinds of information with the vegetative and productive indicators in order to estimate the balance between these two components at each plant level. About the result, we firstly detected the best predictor for this kind of parameters. And after that, we were able to generate the maps on which we have stored the information about the pruning weight, the fruits weight, the balance between the vegetative and productive components at each plant level, but not including the voids inside the field. So this kind of result is very, very important to give to a farmer, which can have a complete overview of the balance inside this field at a resolution of the single plant. So another approach that we have carried out by using the UFV image is similar to that one, but in this case, we have developed a fully automated procedure by extracting the information about the canopy of the plants in a three-dimensional model. So in this case, we have acquired the image of the vineyard by using the same drone, but we use only the RGB channels information, and we fuse the image, so the two-dimensional images, for the three-dimensional reconstruction of the field, as you can see in this animation. And that we extract only the information about the pixel that we previously have selected inside the field, so the 10 sampling areas. So the automatic processing approach involves the ground and on-ground points separation, also in this case by removing the information about the ground points. And to do this, we have developed a closed simulation filter, which automatically removes this kind of information. So the second step was the normalization of the height of the model in order to definitely remove the ground points. So after that, we have implement a procedure using MATLAB for the identification of the single rows, which in this case wasn't done manually as in the previous case. So for the three-dimensional approach, all the pipeline was automatically. So we use a dbScan clustering approach for detecting different clusters inside the three-dimensional model. And after that, we applied a principal component analysis in order to detect the orientation of each cluster and unify the cluster that was inserted in the same row. So as you can see, sorry, in the slide, we correct the disposition of the cluster by inserting the same cluster in the same row, as here is identified by the two different colors. Also in this case, so we also identified the possible voids inside the field. So after that, we want to automatically detect the individual plants. So we another time we implement a PCA analysis in order to detect the orientation and the one set of each rows, and then we divide the row by 90 centimeters, which is the distance between the plants, in order to obtain the theoretical area of each plant. Also, in this case, we correct the errors by considering the minimum points that represent a plant, and then we calculate the distance between the centroid of the detected plants in order to reallocate the points, the erroneous points inside the same plant. So at the end, we had this kind of result. So the three-dimensional model divided into the single plants. And so we were able to extract a series of information about the morphology, so the structure of the canopy at the individual plants level, like the height, the surface, and the volume. And we include this kind of information in allometric equation for the estimation of the indices that I've showed before. So that's the final result. You can see that we obtain reliable prediction about the pruning weight starting from the fruit setting stage. In this case, we have to underline that the green pruning and the senescence affect the results, including the resolution of the three-dimensional model. So the same for the other indexes. We obtain a good estimation for the Rabi indexes starting from the fruit setting, also for the GB index and the RDM index. Didn't allow us to obtain reliable prediction because this kind of index requires vineyard-specific calibration of the coefficient. So we are working on it. So also in this case, we obtain a map about the status of the vineyard by considering the characteristics of the plants at individual plants level. So also in this case, we can provide to the farmers reliable information about the vineyard. So we can switch to the SAR application, which is the last application. In this case, the aim of this work, which is a work in progress work, was the monitoring of the growth of the plants by using the SAR imagery. So we extract several SAR indices from the pixel, from the 10 sampling areas that we have detected, and we also collect the volume data by manual measurements of the plants and also of the grass inside the 10 pixels, and we sum these two kind of information for obtain the total volume of the pixel. So by considering both the volume of the plants and the volume of the grass. And we correlate this kind of information with the indices extract from the satellite images in order to predict and to evaluate from the satellite the evolution of the volume during the growing season. So those are the final results. You can see that the scaled VH minus V parameter is the most effective in capturing the evolution of the volume of the vines. So we can use this kind of index to monitor the growth of the vines by using the satellite imagery. But also, as you can see in the figure number B, there is a negligible interference from the inter-row vegetation signal because the correlation was not so good. So once validated, this approach could offer valuable insights into the drug development. So we are working on this kind of approach by applying this kind of methodology for the second growing season, because these results refer just to a single growing season. I would like to acknowledge all the people that contribute to obtain this result. Also, I would like to thank you for your attention, but this is not the end, because I have included two easy practical application, as I mentioned at the beginning of this presentation. So I have to switch to the other softwares. Okay, the first application is the obtainment of a height map by using the two-dimensional reconstruction of the field. Sorry. The first step is the reconstruction of the two-dimensional model, starting from the two-dimensional images that we have acquired by using our drone. I'm using the IGSoft MetaShape software that allow us to automatically reconstruct the two-dimensional model. The first step is the upload of the individual two-dimensional images, as you can see here. Sorry. The second and third step is the reconstruction of the three-dimensional model. The first one is the sparse point cloud, and that's the result. Obviously, I have already done it. And the second step is the reconstruction of the dense point cloud. So you can see that now we have a greater resolution, spatial resolution of this model. So when we have acquired and we have obtained our three-dimensional model, we can upload it on another software, which is the Cloud Compare, in order to analyze the three-dimensional model. So the first step is the upload of the model. You have to wait some minutes, so some seconds, not minutes. Okay, so now we have uploaded our three-dimensional model, and for simplicity, we could restrict the area of interest on the left side. So we can directly cut the three-dimensional model in order to identify the area of interest by using this tool. Okay, and we can remove from the software the other side of the video, which we are not interested in. I don't know why it's so. Okay. So now we have our area of interest, and the next step is the filtering of erroneous points, which are, for example, this one, these small points behind the field. And to do this, we can use this kind of tool, so the sort filter, which automatically eliminate this kind of outliers. But in this case, we have to wait some seconds. Okay. Nice. So the next step is the identification of the ground and non-ground points. To do this, we can use the CSF filter, so the cloud simulation filter, by selecting the relief, because our condition is that one. So we have the soil and the plants, and by also incorporating the slow processing action, because this kind of action process also the slope of the three-dimensional model. After, we have to insert some parameters for processing the three-dimensional model, which I have already selected for the optimal detection of the ground and non-ground point. So now we have, as you can see from the two-dimensional model, we have separate the off-ground points and the ground points. So it has been easy to separate. For a better to better understand this kind of process, we can also can duplicate and then merge it. And you can see in blue the points that are referred to the plants, and in red the points that refer to the ground points. So after that, we can also remove another time the error that are include the outliers that are included in this two-dimensional model by using another time the cleaning filter, automatically remove it. Okay, and after that, we have to normalize the soil points in order to obtain a reliable height map of the two-dimensional model. So to do this, we have to rasterize the points that are referred to the ground points. So we have to go to rasterize. Okay, hit create, and we can export the cloud. Now we have rasterized the ground points, and we can select the off-ground points, so the points related only to the plants, the rasterized ground point, and calculate the distances. The reference is the ground point. We can press OK. So now we have our off-ground points, so the points of exclusively of the plants with the real height. So to see it, we can also insert the visible color scale. So you can see that our plants have a height between 0, which is the blue color, and around 2 meters. So those are the real dimension. Here we have some trees at the border of the field which reach 7 meters. So I think that that's all. That was a practical application. I think that my time is ended, so I have concluded my presentation. Sorry. And if you have any question, I'm here to reply you. Thank you.